Hello. Tonight, we're going somewhere very small and very far away. There is a piece of amber golden, cloudy at the edges, warm when you hold it in your palm, sitting in a museum drawer somewhere in the world right now. It is about the size of a marble, maybe smaller, and inside it, suspended in perfect stillness, is an ant. Not quite an ant. Something that became an ant in a world that no longer exists, following rules that evolution has since abandoned entirely. It has jaws, but they don't close sideways the way every ant you have ever seen closes its jaws. They curve upward, like two scythes mounted on a face, and between them projecting downward from its forehead like a fang, a horn, a brace, a counterweight to something it was about to do 99 million years ago, when the resin caught it and the world kept moving without it. Scientists call it Haidomyrmex, the hell ant. Tonight we are going to spend some time with it, with what it was, with the world it moved through, with the science that has slowly, carefully rebuilt its biography from a handful of golden windows, and with the questions that amber, for all its fidelity, still refuses to answer. The story begins as so many strange stories do with a place. Tree resin is not a rare thing. Walk through any pine forest and you will find it sticky, sharp-smelling, welling out of a wound in the bark. A tree bleeds resin the way skin forms a scab. It is a defense. It seals. It traps. It hardens over weeks into something amber-colored and brittle. Most resin does not last. It dries, it crumbles, it is consumed by soil and time within decades. But under specific conditions, burial in oxygen-poor sediment pressure, the slow movement of geological time, resin can survive. It polymerizes. The molecular chains lock together, growing denser, growing harder, shedding volatiles, until what remains is not quite resin anymore. It is amber. The amber found in northern Myanmar, what scientists call Burmese amber, or by its formal name Kachin amber, is among the most scientifically important amber deposits on Earth. Not because of its size, though the deposit is substantial. Because of its age. Radiometric dating places it at roughly 99 million years old. That puts it firmly in the mid-Cretaceous period, a chapter of Earth history so remote that the continents wore different shapes, the oceans traced different coastlines, and the animals walking the forest floors shared almost nothing. With the animals walking them today, 99 million years is a number the mind cannot hold. Put it this way, if you compressed the entire age of that amber into a single calendar year, human civilization would appear in the last 4 seconds of December 31st. Everything we have ever built, everything we have ever named. 4 seconds. The resin did not know it was making history. It simply ran down a wounded tree, caught what it caught, and slowly became stone. What it preserved by accident, by chemistry, by the blind patience of geology, is still being discovered. The Hukong Valley sits in Kachin State, in the far north of Myanmar, pressed between mountain ranges and cut through by the Chindwin River. It is remote. It is dense. It is the kind of landscape that swallows roads and resists easy description. The valley has another name. During the Second World War, Allied soldiers marching through it in retreat called it the Valley of Death, not metaphorically. The conditions killed them: heat, disease, terrain, and the weight of everything they were carrying. The name stayed. Today, the valley contains something else it has always contained, though the world only began paying close attention in the late 20th century. Amber, buried in shallow mines, pulled out in rough chunks by local workers, sorted and traded through a supply chain that stretches from muddy hillside excavations to museum collections in Europe, North America, and China. The amber mines are not deep industrial operations. They are hand-dug, seasonal, worked by people for whom the amber represents income in a region with few alternatives. A piece with an insect inside, a good inclusion, is worth more than a piece without. A piece with something unusual is worth considerably more. This market pressure shapes what gets excavated, what gets preserved, and eventually what gets studied. The valley itself is lush, dense canopy, high humidity, the kind of green that feels almost aggressive. It is not difficult to imagine standing there that something very old is in the ground beneath your feet. Something is. A great deal of something. The path a piece of Burmese amber travels from the ground to a scientist's microscope is rarely straightforward. It does not begin in a laboratory. It begins in a market. After extraction, raw amber is typically sold to local dealers who sort it by size, clarity, and the presence of inclusions. Pieces with visible biological material, a wing, a leg, a whole insect body, command higher prices. From local dealers, the material moves upward through a trade network that has operated for decades, eventually reaching gem markets in Mandalay and Yangon, and from there into the international trade. Scientists access Burmese amber in several ways. Some specimens are purchased directly from dealers, institutions, and individual researchers buying material through the commercial market. Some arrive as donations. Some are found in existing museum collections acquired decades ago before the current scrutiny around the amber trade had developed. A smaller number enter through more formal arrangements with local authorities, though this pathway is complicated by political circumstances that have shifted considerably in recent years. Once a specimen reaches a researcher, it is typically trimmed carefully, using fine abrasives to bring the inclusion as close to the surface as possible without breaching it. The goal is clarity. Amber is not perfectly transparent. It has inclusions of its own bubbles, cracks, suspended debris, and getting a clean optical path to a specimen a few millimeters across requires patience and precision. Then it goes under a microscope, and that is when the work begins. Burmese amber did not arrive in science suddenly. It crept in over the course of a century and a half through a series of incremental recognitions, each one expanding the scientific community's sense of what the deposit contained. European naturalists were documenting amber inclusions from Myanmar as early as the mid-1800s, though the material was often misidentified, misdated, or simply filed away without deep analysis. The tools did not yet exist to understand what was being held. The insects described in those early papers were noted as curiosities, interesting perhaps, remarkable in some cases, but the full weight of the deposit's age and what that age implied about the organisms inside was not yet calculable. Through the 20th century, interest grew in pulses. Each improvement in microscopy, each refinement in radiometric dating, each new taxonomic framework brought Burmese amber back into focus. By the 1990s, the scientific community had begun to appreciate that this deposit was not merely old. It was old in a way that placed its organisms at a genuinely pivotal moment in the history of life. On land, the mid-Cretaceous, when flowering plants were beginning to diversify, when insects were in the middle of their great co-evolutionary experiment with those plants, and when ants as a group were still a new idea. Hell ants are a product of that moment. They were already specialized, already refined, already hunting with curved jaws before the world they lived in had yet decided what it was becoming. Scientists still debate the precise stratigraphic age of some Burmese amber layers. Not all material from the deposit dates to the same moment, and calibrating the differences matters enormously when you are trying to place organisms in evolutionary sequence. There is something that happens when a person holds a piece of amber with an insect inside. The material itself is lighter than it looks. Amber has a density close to that of hardwood, not the cold heaviness of stone, not the warmth of metal. It sits in the hand like a large grape, like something almost organic, which in a sense it is. It is warm. Amber conducts heat poorly, so it takes on the temperature of whatever is touching it and holds it. A piece that has been in your hand for 30 seconds feels like your own skin. Stone never does that. Then there is the looking. Tipping the piece to find the angle where the inclusion sharpens, where the wing or the leg or the entire body comes into focus through the amber matrix. The experience is genuinely strange. You are not looking at a photograph. You are not looking at a reconstruction. You are looking at the actual original, physical surface of an animal that has not been touched by open air for longer than the human species has existed. Researchers who work with amber inclusions describe this sensation in various ways. Some treat it as purely instrumental. The specimen is data and the task is extraction. Others are more candid. There is a vertigo in it, they say, a brief irrational sense of proximity to something impossibly far away. You might understand that feeling if you have ever picked up an old photograph of someone you never met and felt for a half second that they were almost there. The ant in the amber is closer than that photograph, closer in physical terms than almost anything else from its time, and stranger. The formal scientific description of Haidomyrmex as a genus appeared in 2003 in a paper by the Russian entomologist Alexander Raznitsin and his colleague Michael Dlusky. The specimen they described had been sitting in a collection known, examined puzzling before anyone had the framework to place it. That is how taxonomy often works. The animal does not wait for a name. The name waits for someone with enough context, enough comparative knowledge, and enough certainty to commit it to the scientific record. Naming a new genus is not a casual act. It is a formal claim about the structure of life, a statement that this organism represents something distinct enough to require its own category. The jaws made the case immediately. Raznitsin and Dlusky recognized that the upward curving mandibles combined with the clypeal horn, the projection from the face represented a functional system unlike anything in the living ant fauna, and unlike the earlier, more primitive ants already known from amber. This was not a primitive ant that happened to look odd. This was a derived, specialized predator. Specialized in a direction that evolution had apparently since abandoned. The paper was careful. It acknowledged what could not yet be known. It asked questions it could not answer. That tentativeness, that rigorous humility is part of what makes the hell ant literature interesting to read. The scientists working in this space rarely overclaim. A creature this strange deserves careful language. Alexander Raznitsin spent his career at the Paleontological Institute in Moscow building what became one of the most comprehensive frameworks for understanding fossil insect evolution in the world. His work spanned hundreds of extinct species across dozens of orders. He was not someone who named things casually. Michael Dlusky was a specialist in fossil ants, specifically a narrower focus and in some ways a more demanding one. Ants are extraordinarily diverse. Their morphology overlaps in complex ways. Distinguishing genuine novelty from surface variation requires deep comparative knowledge, the kind that takes decades to build. Together, they were well positioned to recognize what the hell ant specimen represented. Raznitsin's breadth gave the wider context where this fit in the insect record what it implied about predator evolution in the Cretaceous. Dlusky's depth gave the ant-specific framework what features in living and fossil ants are ancient versus derived, what jaw architectures had been tried, which had persisted. Their 2003 description was not the end of hell ant science, it was the opening of a door. Subsequent researchers working from additional specimens, improved imaging technology, and expanded phylogenetic methods have refined, revised, and extended their original work considerably. But the name they gave it held. As names in science sometimes do, not because they were the first to see the creature, but because they were the first to see it clearly enough to say with confidence that it was something new. The name Haidomyrmex is built from two Greek roots. Haido from Hades, the Greek underworld, the realm of the dead, a place of shadows and permanence. Myrmex ant, hell ant. Scientific names are not usually poetic. They are functional, a stable label that survives translation, that carries information about taxonomy or morphology that resists the drift of common language. Haidomyrmex is an exception. It is functional and evocative in equal measure. The Hades reference does several things at once. It gestures at the ant's apparent fearfulness, those upward jaws, that face horn, that posture frozen mid-hunt. It gestures at antiquity Hades as the deep past the underworld, as the place things go and do not return from. And it gestures, perhaps unconsciously, at the experience of finding the creature, something surfacing from an ancient buried world, carrying the look of a place that should not have living things in it. The broader group of hell ants, the tribe Haidomyrmecini, carries the name further. Every genus in the tribe is a variation on the same dark theme. Ceratomyrmex, the horned ant, Linguamyrmex, the tongue ant, Aquilomyrmex, the eagle ant, each name reaching for something fierce, something angular, something old. Names matter. They shape how a thing is remembered. The hell ants, whatever their actual behavior was, have been given a mythology to live inside. Whether that mythology fits them, Whether they were truly fearsome or simply specialized in a way that reads as fearsome to modern eyes is a question the amber cannot yet answer. Haidomyrmex was small. The body length of known specimens ranges roughly from 3 to 5 millimeters, the larger individuals, about as long as a single lowercase letter on a printed page. The width of a pencil eraser, the distance between two ridges on a fingerprint. This matters because the jaws, those remarkable curving upward-pointing mandibles, are not the tools of something large. They are the tools of something tiny hunting, something tinier still. The drama of the hell ant's anatomy is compressed into a space smaller than a grain of rice laid lengthwise. There is something cognitively useful about calibrating this. When we imagine predators, we tend to think in terms of scale, the lunge of something large enough to cause damage. The hell ant's entire killing apparatus from jaw tip to clypeal horn spans less than 2 millimeters. Its prey, by implication, was measured in fractions of a millimeter. The violence here was miniature, which does not mean it was gentle, but it does mean it was invisible to anything larger than a spider. Burmese amber specimens preserve the hell ant at its actual physical scale, no magnification built into the fossil itself. Under a standard hand lens, the animal is a faint, legged shape in gold. Under a research microscope, every surface feature comes into resolution. The gap between those two views is the gap between knowing an animal exists and beginning to understand what it was. All ants share a fundamental body plan. 3 tagmata, the 3 major body regions that define insects: head, thorax, abdomen. In ants, the abdomen is divided by a specialized waist structure, the petiole, into 2 functional zones. The front section contains the abdomen's forward segments. The rear section, the gaster, houses the digestive and reproductive organs. This plan is ancient. It is recognizable in every living ant species: in the fire ant on a sidewalk, in the leafcutter ant crossing a Costa Rican trail, in the army ant column moving through a jungle in absolute silence. The architecture is stable because it works. Haidomyrmex is built on this same plan. Head, thorax, petiole, gaster, the landmarks are all present. An entomologist looking at the amber specimen would recognize immediately what they were holding: an ant. But the deviations are immediate and significant. The head does not sit atop the thorax the way a modern ant's head does. It tilts forward, angled downward, the face projected ahead rather than oriented to look forward. The petiole is sharply defined, almost architectural in its narrowness. And the head itself carries the modifications that define the genus: the jaws that do not close sideways, and the horn that projects from the face. These are not primitive features. They are not the remnants of a body plan that hadn't yet figured itself out. They are refinements, a design that had been worked on in evolutionary terms, that had been selected for generation by generation because it worked. It worked in a world that no longer exists. What it worked on, that question comes next. Tilt your head forward. Not a nod, a sustained forward lean chin toward chest, the crown of your skull aimed at the ceiling. Hold that. Now imagine hunting from that position. Imagine that this is not a strain, not a posture you are forcing, but the resting position of your skull, the angle your neck was built for, the orientation your eyes were designed to use. That is the head of Haidomyrmex. In living ants, the head sits roughly level with the thorax or angles slightly upward. The eyes face forward or to the sides. The mandibles, when open, spread laterally, creating a grasping arc in the horizontal plane. The whole arrangement is built for a world encountered face forward. The hell ant's head is canted forward so that its face, its mandibles, its clypeal horn, its entire functional front surface points downward and ahead. Not dramatically, not grotesquely, but measurably consistently, in a way that no living ant replicates. Researchers measuring the angle in multiple specimens find it is not an artifact of preservation, not a distortion created by the amber. It is anatomical, built in. What does a forward-tilted head imply? It implies a hunting posture oriented towards something below, something on a surface the ant was walking on, or clinging to something at roughly the level of the ant's own feet. The jaws curving upward from that downward angled face would then arc toward the animal's own body, toward the horn waiting above them. The geometry is deliberate. The geometry is a trap. Scientists still debate the precise hunting posture Haidomyrmex adopted, whether it approached prey from above, from the side, or from beneath a substrate. But the head angle is not debated. That angle is the first thing any researcher notices, and it does not let you go. The petiole, the waist of an ant, is one of the defining features of the group. It is not merely a narrowing, it is a structural joint, a flexible connector between the thorax and the gaster that allows the abdomen to rotate, to curl, to aim. In stinging ants, this flexibility is what allows the gaster to swing forward and deliver venom. In all ants, the petiole's mobility is part of what makes the body plan so adaptable. Haidomyrmex has a petiole that is sharply defined, narrow and distinct in a way that is clearly visible in amber specimens, even without magnification. Under a microscope, it is almost architectural, a precise constriction like something engineered. What does a sharply defined petiole imply in a predatory ant? Mobility. The gaster could swing. The abdomen could position itself independently of the thorax. In an ant that may have produced venom and hell, ants are believed to have possessed venom glands, though direct evidence is limited that mobility would have been part of the killing sequence. Here is the picture that begins to assemble a small animal head, angled downward and forward, jaws curving up, horn projecting down waist, flexible enough to curl the gaster forward if needed. Every feature pointing toward a single moment of contact. Every feature built around the capture of something alive. The petiole is easy to overlook. It is not the dramatic feature, not the jaws, not the horn, but it is part of the architecture. And architectures, when they are this consistent, are not accidents. There is a specific quality to amber preservation that stone fossils do not have. Stone compresses. Stone flattens. Stone takes a three-dimensional body and renders it in 2 dimensions. The way a pressed flower is still a flower, but is no longer quite itself. Amber does not compress. It encases. The body inside an amber inclusion retains its 3-dimensional form, its actual posture, the actual angle of every limb, the actual curvature of the antennae at the moment of entrapment. The Haidomyrmex specimens preserved in amber are caught in postures. Not death postures, or not always. Some specimens appear to be in mid-movement. Legs not folded in rest but extended, displaced, caught between one position and another. Antennae angled forward. The body's axis tilted in a way that suggests forward motion interrupted. This is one of the uncanny aspects of working with amber inclusions. The specimens are not dead in the way a stone fossil is dead, fixed, abstracted, reduced to impression. They look paused. They look like something that could, if the amber simply dissolved, resume what it was doing. The overall silhouette of Haidomyrmex in amber, that forward-tilted head, those upward jaws, the narrow waist, the compact gaster, reads as purposeful. Even frozen. Even at 99 million years of remove, it reads as an animal that knew what it was doing. Whether it did in any sense we would recognize as knowing is a question better left to philosophers. What the silhouette tells the biologist is enough. The number of confirmed Haidomyrmex specimens is small. Estimates across the published literature suggest fewer than a dozen well-documented individuals attributable to the genus, a figure that sounds modest until you consider that each one is 99 million years old physically, intact and irreplaceable. They are scattered. Some are held in European Natural History Museum collections, institutions that acquired Burmese amber material over the course of the 20th century through purchase, donation and research exchange. Some are in North American university collections. Some reside in Chinese institutions, which have become increasingly significant in Burmese amber research, as proximity to the source material has made Chinese researchers prominent in the field. The distribution matters scientifically. A specimen held in one country may be available to a researcher in another only through collaboration, through loan agreements, or through imaging data shared between institutions. High-resolution micro-CT scanning, the technique that allows researchers to generate 3-dimensional digital models of amber inclusions without physically cutting them, has partially addressed this problem. A scan can travel instantly. The specimen cannot. The number of hell ant specimens across all genera in Haidomyrmecini is larger, perhaps several dozen, but still vanishingly small relative to the diversity questions researchers want to answer. For comparison, a single ant colony of some living species contains millions of individuals. Science is building its understanding of an entire predatory lineage from a handful of frozen bodies, each smaller than a sunflower seed. The patience that requires is considerable. Ask a paleontologist what it is like to work with amber inclusions, and you will often get a pause before the answer. Not because the answer is complicated, because it is surprisingly personal. The physical act of examination, positioning the amber under a stereomicroscope, adjusting the illumination angle, bringing the specimen into focus is technically routine. Researchers do it hundreds of times. It becomes procedure. What does not entirely become procedure is the moment the animal sharpens into resolution. Because amber is not a photograph. There is depth. There is three-dimensionality. You are looking through a medium through cloudy gold, at a surface that is genuinely physically there. The cuticle of the ant's head, the texture of the jaw's inner surface, the precise geometry of the clipial horn, its tip, its angle. One researcher describing the experience informally compared it to looking at someone through a frosted window. You know they are there. You can almost see them completely. The glass is the only thing between you. Except the glass, in this case, is 99 million years thick. The experience is not sentimental, not for working scientists who have papers to write and hypotheses to test. But it is not entirely neutral either. These researchers are spending their professional lives in close proximity to something that should, by any ordinary reckoning, be completely gone. The fact that it is not the fact that the amber held produces something. Call it a quiet gratitude toward geology. Every feature of Haidomyrmex that identifies it as an ant, the petiole, the geniculate antennae, the 6 legs, the overall tagmata, is present and recognizable. There is no ambiguity about the group. This is an ant. And yet nothing about the face is familiar. The jaws alone disqualify it from everything in the living fauna. No living ant species across the more than 14,000 described species on Earth today possesses mandibles that curve upward. The design is structurally possible, Haidomyrmex proves that, but it has not been reinvented. Not once across the entire modern ant diversification. Across millions of years of subsequent evolution has any lineage stumbled back toward the upward curving jaw. That absence is information. When evolution does not rediscover a design, it usually means one of two things. Either the design requires a very specific set of conditions that no longer exist, or it was not ultimately a winning strategy, and the lineages that carried it are gone, leaving a gap that nothing has filled. The hell ant face produces a specific cognitive effect in people who encounter it for the first time. There is recognition, yes, ant, followed immediately by wrongness. The wrongness is not just aesthetic, it is functional. You can see, even without understanding the biomechanics, that this face is built to do something that no living ant face is built to do. You can see that the design has a purpose. You just can't at first glance see what the purpose is. That is the uncanny valley of paleontology. Familiar enough to categorize. Strange enough to unsettle. Haidomyrmex is not alone. It belongs to a tribe, a taxonomic grouping one level above genus called Haidomyrmecini. And within that tribe, the variations on the upward jaw theme are remarkable in their diversity. As of the most recent published surveys, Haidomyrmecini contains somewhere between 8 and 12 genera, depending on how certain disputed specimens are classified. And that number has grown steadily as new amber material is examined. Each genus represents a distinct variation on the core hell ant design. Upward curving jaws, yes, but the specific geometry of the curve differs. The clipial horn varies in length, in curvature, in apparent rigidity. The head shape varies. The proportions of the body vary. What the tribe shares is the functional logic. The trap, the upward jaw paired with a downward projecting facial feature, creating a closing mechanism that works on a vertical axis rather than a horizontal one. This is not convergence, multiple unrelated lineages independently arriving at the same solution. This is a single lineage diversifying around a single core innovation, exploring the design space of one very specific way to catch things and kill them. The genera include Haidomyrmex, which provided one of the most spectacular amber specimens in hell ant science, a subject we will return to, as well as Haidomyrmex, Haidomyrmex, Haidomyrmodes, and others. each one a window into a slightly different version of the same dark idea. Taken together, the tribe represents not a failed experiment but an entire adaptive radiation, a whole branch of the ant family tree that grew diversified and then stopped completely. Some scientific names escape the literature. They cross over into science journalism, into documentary narration, into the kind of casual conversation people have after reading something interesting. Haidomyrmex has made that crossing. The hell ant is, by the standards of obscure Cretaceous entomology, remarkably well known. The name is part of it. Hell ant. 2 words, Anglo-Saxon and direct, carrying the full weight of their meaning without decoration. It does not require a mythology degree to feel what those words are doing. Hell, a place of ancient darkness and permanence. Ant, a creature so ordinary it borders on invisible in daily life. The collision of those 2 registers is immediate and effective, but the name works because the animal earns it. If Haidomyrmex looked like a slightly odd version of the ants in your kitchen, the name would feel overwrought. It doesn't. The upward jaws, the facial horn, the forward tilted head, the creature looks to the non-specialist like something that was designed in a nightmare and preserved in amber, so the nightmare wouldn't be forgotten. That impression is not entirely fair to the animal. It was not fearsome in any absolute sense. It was small. It hunted things smaller than itself in a forest that no longer exists for reasons that served its own survival and nothing more. But the impression persists because appearances carry meaning even when meaning was not intended. The hell ant got a good name. And in popular science, where the name is often the difference between an animal that enters the public imagination and one that remains in a journal footnote, a good name matters more than almost anything else. Here is where the uncanny begins in earnest. Pick any living ant, any species from any continent, from any ecological niche. The Argentine ant invading your pantry. The trapjaw ant of the tropics, which can snap its mandibles shut faster than almost any other movement in the animal kingdom. Every single one of them closes its jaws on the same axis, sideways. The mandibles arc inward from either side of the head, meeting at the midline. The motion is horizontal, a lateral closure like 2 arms reaching toward each other. This is the ant jaw. It is so universal that it reads as definitional, not a feature of some ants, but a feature of ants as a category. Haidomyrmex closes its jaws on a different axis entirely. The mandibles do not arc inward from the sides. They curve upward, away from the horizontal plane, rising from the front of the head in a shape that can only be described as a scythe, or a pair of scythes, mounted symmetrically on either side of the midline and aimed at the sky. The motion implied by this geometry is not a horizontal closure. It is a vertical sweep. The jaws, snapping shut, would not close toward each other from the sides. They would rotate upward and inward, rising from below to meet something above the head. Something above the head that is being held in place by the horn, projecting downward from the face. The machine, when you see it whole, is unmistakable, and once seen it cannot be unseen. 14,000. That is the approximate number of described living ant species, and the true number, including undescribed species, is estimated to be considerably higher. Ants have colonized every continent except Antarctica. They have evolved to farm fungi, to herd aphids, to build cities of 100 million individuals, to raid and enslave other ant species, to bivouac in living masses, to navigate by the sun. The variety of ant life is staggering. Not one of those 14,000 species has upward curving mandibles. This is worth sitting with. Evolution is a process that explores possibility exhaustively. If upward curving jaws were a broadly viable design for ants, if the functional logic of the hell ant trap were applicable across a wide range of prey and environments, we would expect to see it reinvented. Evolution reinvents things constantly. Eyes have evolved independently more than 50 times. Wings have appeared in multiple unrelated lineages. The streamlined body plan of a fast swimmer has been arrived at by fish, dolphins, and ichthyosaurs. The upward curving ant mandible has appeared exactly once, in one tribe, in one narrow window of geological time, in one ecological context that no longer exists. Some researchers believe this tells us the design was exquisitely fitted to a prey type that vanished. that the mandible geometry was so specific to a particular target that when the target disappeared, the design became non-viable and the lineage followed. Others suggest the design had inherent limitations that made it vulnerable to competition from the more versatile horizontal jaw architecture that dominates modern ants. Both hypotheses may be true, both may be incomplete. The honest answer for now is that we don't fully know. And 14,000 living species, not one of which repeated the experiment, suggest the question is worth asking carefully. A scythe is not a random shape. It is a solution. The curve distributes force along the blade's length, allowing a single sweeping motion to cut through resistance that a straight edge would bind against. The arc is functional. Every point on the curve serves the motion. The mandibles of Haidomyrmex follow a similar logic, though the motion they were built for was not cutting grain but catching prey. Each mandible curves upward from its base at the front of the head, rising in an arc that brings the tip to a point positioned above and slightly behind the ant's own head. The curve is not uniform, it tightens toward the tip the way a fishhook tightens, concentrating the geometry at the point of contact. The tips themselves are sharp. Under microscopy, the terminal points of hell ant mandibles show fine acute terminations, not the broad-toothed edges of crushing jaws, not the serrated inner surfaces of slicing jaws, but narrow points designed to penetrate, to pierce, to hold. The inner surface of the mandible, the face that would contact prey, varies across hell ant genera. In some it bears fine teeth or denticles along the curve. In others it is smoother, relying on the geometry of the grip rather than surface texture to retain a struggling animal. Haidomyrmex itself shows features along the inner mandible surface that suggest the grip once made was not easily broken. Think of the arc of a crab's claw, not the broad, crushing claw, but the slender, precise claw, the one built for catching, not for breaking. The hell ant mandible is closer to that, a catching instrument designed around the moment of contact, everything afterward, downstream from that first irreversible pierce. The clypeus is a plate on the front of an insect's head, a structural region that in most ants is relatively unremarkable, flat or gently curved. Part of the face's architecture without being its defining feature. In Haidomyrmex, the clypeus is not unremarkable. It bears a projection. A horn, not a horn in the rhinoceros sense, not a single large protrusion, but a downward-pointing process extending from the lower margin of the clypeal plate aimed toward the space below the ant's head. Toward the space, the upward-curving mandibles are sweeping through. The horn is the counterbrace. Without it, the upward mandibles would sweep through open space, a catching motion with nothing to catch against. The horn provides the fixed point, the upper limit of the trap. When the mandibles swing upward, prey caught between them, and the horn has nowhere to go. The geometry closes on all sides. This is the part of the hell ant anatomy that took the longest to fully appreciate. Early descriptions noted the horn, but were uncertain of its function. Was it structural, sensory, incidental? It was the biomechanical analysis combined with the eventual discovery of a specimen caught mid-hunt that clarified the horn's role beyond reasonable doubt. The horn is not incidental. It is load-bearing not in the structural sense but in the functional sense. It is the anvil to the mandible's hammer, the fixed point that makes the moving parts meaningful. Across hell ant genera the horn varies. Some are long and slender, some are broad and paddle-like, some curve forward. The variation suggests that different genera were fine-tuning the same basic trap for different prey dimensions, adjusting the gap, adjusting the angle, calibrating the mechanism to a specific target size. The trap is elegant, not in a way that inspires warmth, but in the way that a well-designed lock is elegant or a precisely calibrated instrument. Every part serves every other part. Nothing is excess. Here is the sequence as biomechanical analysis has reconstructed it. The hell ant approaches prey, a soft-bodied insect most likely small enough to fit in the space between jaw tip and horn. The head is angled forward and down, the horned face positioned above the target. The mandibles are open, extended downward and outward, framing the prey from below. Between the mandibles beneath and the horn above. Then the mandibles close. They sweep upward that vertical arc, and the prey is driven upward into contact with the horn. Impaled or pinned or held, the exact mechanism of injury depends on the prey's body and the gap geometry. The horn prevents escape upward. The mandibles prevent escape downward. The ant's own head is the walls of the trap. What happens next, whether venom is delivered, whether the prey is consumed immediately or carried, is not preserved in the specimens we have. The amber catches the architecture, but not the aftermath. What the architecture tells us is enough to say this was not a generalist predator. A generalist predator has tools that work on many things. The hell ant's trap is calibrated for a specific size range, a specific body type, a specific moment of vulnerability. Something in the Cretaceous forest was being hunted in exactly this way, and had been hunted this way long enough for the trap to become this refined. Whatever that prey was, it was part of a relationship, a very old one. Reconstructing the biomechanics of an extinct animal from amber is not guesswork. It is constrained inference working from physical evidence toward functional conclusions, with explicit acknowledgement of where the evidence runs out. For hell ants, the primary evidence is geometric. The angle of the mandibles, the position of the muscle attachment, points visible on the inner surfaces of the head capsule, the length and curvature of the jaw, these are data. Muscle cross-section can be estimated from the attachment scar area. Mechanical advantage can be calculated from the lever geometry. Force output can be approximated. What these analyses suggest is that the hell ant jaw was not built for crushing. The long curved mandibles, the attachment geometry, the arc of motion, these point towards speed and reach rather than raw compressive force. The trap was built to close fast and hold firmly, not to break. This is consistent with hunting soft-bodied prey. A hard-bodied beetle larva, a heavily sclerotized insect, these would require crushing force, and the hell ant jaw is not the right instrument for that. A soft larva, a caterpillar analog, a slow-moving grub, these require only capture and retention. Speed matters more than strength. Reach matters more than power. The biomechanics also suggest the strike was quick. The muscle geometry implies a fast twitch, high-velocity closure, the kind of motion that works as an ambush tool. Wait for proximity, strike, hold. Scientists are cautious about over-interpreting these models. The assumptions built into biomechanical reconstruction are real, and the error bars are wide. But the broad conclusion, fast-reaching, retentive rather than crushing, is considered reasonably robust. The trap was built to catch, not to destroy on contact. The prey question is the most tantalizing unanswered question in hell ant biology. And it is unanswered in a specific way, not because there is no evidence, but because the evidence is indirect, and indirect evidence in paleontology requires humility. The trap geometry constrains the possibilities. The prey had to fit in the space between mandible tips and clypeal horn, a gap that in Haidomyrmex was probably on the order of 1 to 2 millimeters in its resting position. This rules out anything large. The prey had to be worth catching, energetically valuable enough to justify the metabolic cost of the strike. This rules out things too small to handle. The prey had to be soft-bodied, or at least soft-bodied enough that piercing capture without crushing force was effective. Hard, sclerotized insects, beetles for example, would be poor targets for this mechanism. Larvae nymphs, soft-bodied flies, early and star insects of various kinds, these fit the profile. The Burmese amber fauna itself offers candidates. The deposit contains a remarkable diversity of soft-bodied invertebrates, early flies, larval forms, small vermiform creatures, any of which could theoretically have served as prey. But without a specimen caught in the act of being consumed, the identification remains speculative. Perhaps the most intriguing hypothesis, and it is a hypothesis not a conclusion, is that hell ants targeted insect larvae specifically. Larvae are soft, slow, energy-dense, and present in predictable locations. A predator that specialized in larvae would need exactly the kind of trap the hell ant possessed: fast, precise, retentive, calibrated to small and yielding targets. What that prey was exactly remains one of the amber's best-kept secrets. The case for soft-bodied prey is not built on a single observation. It accumulates from several directions, each one adding a layer of probability without reaching certainty. First, the jaw geometry. As established, no crushing capacity, high-speed closure, piercing tips. This is a catching instrument designed for yielding targets. The physics exclude hard prey. Second, the horn. The clypeal projection functions as a brace against something being pressed into it. A rigid sclerotized insect would resist this pressure and potentially damage the horn or destabilize the ant's grip. A soft body would deform, would press against the horn surface and hold the way clay holds an impression. Soft prey is not just a plausible target, it is the target the horn was designed to receive. Third, the ecological context. The mid-Cretaceous forest was alive with soft-bodied invertebrates. Early flies, primitive moths, larval forms of beetles and other holometabolous insects. The amber preserves them alongside hell ants because they shared the same forest. They were there. They were the right size. They were soft. Fourth, and this is the most speculative layer, the specialization itself implies prey predictability. A trap this calibrated does not evolve against prey that varies widely in size and texture. It evolves against prey that is consistently available, consistently sized, consistently catchable in the same way. Soft insect larvae present year-round in bark and leaf litter fit this profile better than almost anything else in the Cretaceous fauna. None of this is proof. Paleontology rarely offers proof. It offers evidence converging from different angles, building probability. The probability here points clearly, though not exclusively, towards soft, small, slow, and abundant. Specialization is a gamble. Every lineage that narrows its ecological niche, that commits to a specific prey type, a specific habitat, a specific set of conditions, gains efficiency at the cost of flexibility. The gain is real. A highly specialized predator can exploit its niche more effectively than a generalist could. The cost is also real if the niche disappears. The specialist has nowhere to go. The hellant mandible is specialized. This is not a tool that can pivot. The upward curving jaw, the clypeal horn, the entire trap architecture. These features are deeply committed to a specific mode of predation. An ant with these jaws cannot shift to seed gathering if prey becomes scarce. It cannot switch to fungus farming. It cannot follow its food source into a new ecological context, because the food source and the trap are matched too precisely. This is the specificity problem, and it matters enormously for understanding why hell ants are extinct. Living ant species with highly specialized diets, army ants that eat almost exclusively other social insects, for example, are vulnerable in predictable ways. When their food source fluctuates, they fluctuate with it. When their food source collapses, the collapse cascades. Hell ants were probably more vulnerable than most. The trap implies a prey type. The prey type implies an ecological context. The ecological context, the mid-Cretaceous forest with its specific fauna and flora, is gone. When it went, it likely took the hell ant's food source with it. And when the food source went, the trap became useless. A perfectly designed instrument rendered obsolete by the disappearance of the problem it solved. The Cretaceous was not short of specialized predators. The amber record preserves a remarkable menagerie of extinct hunting insects, each one a solution to the problem of catching living things in a world before the modern fauna existed. There were ancient assassin bugs, distant relatives of the modern predatory Reduviidae, with piercing beaks already recognizable in their basic form. There were primitive mantis-like insects that were neither mantises nor praying mantids, but something adjacent occupying similar ecological roles. There were parasitic wasps of extraordinary variety. Their ovipositors adapted to reach through bark or plant tissue to lay eggs on paralyzed hosts. Among these hell ants occupy a distinctive position. They are not the only predatory insects in the amber. They are not even the only ants. Other early ant genera, from Burmese amber, pursued prey with more conventional jaw designs. What distinguishes hell ants is the degree of commitment in their anatomy. Other predatory insects from the period show specialized features. Hell ants show a completely integrated predatory system, every component of the face working in concert. In the broader history of predatory arthropods, the vertical closing jaw has appeared before in some extinct chelicerates lineages in early arachnid relatives, but never with the specific hell ant geometry and never in an ant. The hell ant trap is genuinely novel. Not without precedent in the broadest evolutionary sense, but without a close analogue in any lineage that has persisted. They were in their moment the most precisely engineered small predators in their forest. That precision was their identity. It was also ultimately their limit. If you want a living ant that gestures toward hell ant predation, and the gesture is only approximate, the trap-jaw ant is the closest candidate. Several living ant genera possess jaws that can snap shut with extreme speed, among the fastest movements recorded in biology. The trap-jaw ant, Odontomachus, for example, can close its mandibles in less than 1 millisecond, generating forces that can launch the ant's own body into the air as a side effect. The jaws move so fast that their closure approaches the physical limits of muscle contraction. But the comparison breaks down at the geometry. Trap-jaw ants close their jaws on the horizontal axis, the conventional ant closure just executed with extraordinary speed. The speed is the novelty. The axis is standard. Hell ant jaws close on the vertical axis. The geometry is the novelty. We cannot know the speed. There is also a behavioral difference that may be more significant than the anatomical one. Trap-jaw ants are known to use their jaw snap defensively as well as offensively, launching themselves away from threats, ricocheting off surfaces to escape predators. The hell ant trap, by contrast, was almost certainly not a defensive mechanism. The horn limits the jaw's function to forward-aimed capture. Defense would require a different architecture. The trap-jaw ant is a useful comparison because it demonstrates that extreme jaw specialization is viable in ants, that committing deeply to one mode of attack is not inherently fatal as an evolutionary strategy, but it is not a model for hell ant behavior. It is a reminder that evolution finds the same problem, how to catch fast prey, and solves it differently every time. A body frozen in amber is not just an anatomical specimen. It is a behavioral record, a single frame from a film that ran for millions of years, caught by accident, preserved by chemistry. The postures of Haidomyrmex specimens vary, but certain features recur. The antennae in multiple specimens are directed forward, extended ahead of the body, in a position consistent with active sensory engagement. Not folded at rest. Not swept back. Forward as if tracking something. The legs in several specimens show asymmetric placement, one side slightly more extended than the other, consistent with motion, interrupted mid-step. Not a resting posture. An ant going somewhere at the moment the resin caught it. The head angle, that forward tilt, is present in all specimens, confirming it is not positional artifact. It is the anatomy, and in the context of forward-directed antennae and mid-step leg placement, it suggests an animal actively engaged with its environment. Scanning, moving, hunting perhaps, or patrolling the surface of a tree trunk. Antenna tips reading the chemical landscape for the signature of prey. Amber catches what was happening, not what typically happened. A single specimen in a single posture is not a behavioral study. But when multiple specimens show consistent postural features, forward antennae, mid-stride legs, head angled toward the substrate, the pattern becomes informative. The hell ant, in its last preserved moments, was not resting. It was working. Whatever it was doing when the resin fell, it was not standing still. Two strategies dominate predatory insect life. The ambush, stillness, patience, proximity, the sudden strike from a fixed position, and the pursuit movement, tracking the sustained effort to close distance on something that does not want to be closed on. The hell ant anatomy speaks to this question, though not with a single clear answer. The forward-tilted head and the trap geometry favor ambush. An ambush predator does not need to run prey down. It needs to be close enough at the right moment for the strike to reach. The hell ant trap is a short-range instrument. The mandibles, even fully extended, cover a distance of only a millimeter or two. This is not the reach of a pursuit predator. This is the reach of something that was already there when the prey arrived. The leg posture in amber specimens, mid-stride directional, complicates the picture. An animal frozen while moving is not an animal that spent its life sitting still. Some active locomotion was clearly part of the behavioral repertoire. The question is whether that movement was patrol covering territory to find ambush positions or pursuit actively following detected prey. The antennae position directed forward suggests active chemosensory engagement. Ants navigate their world, largely through chemical signals and forward-directed antennae, are consistent with an animal tracking a chemical gradient. Tracking a gradient means following it. Following it means moving towards something. The most parsimonious interpretation given all of this is a mixed strategy. Active patrol to locate prey, followed by a final approach to striking range, followed by an ambush-style strike at close quarters. Many modern predatory ants use exactly this combination. Slow pursuit, close approach, one fast moment, then stillness again. Insect eyes come in two functional categories. Compound eyes, the multifaceted structures that dominate the insect head, provide wide-field motion detection and reasonable spatial resolution. Simple eyes, or ocelli, the small, often three-pointed clusters on the top of the head, detect light intensity and aid in orientation, particularly in flight. Haidomyrmex specimens show compound eyes that are relative to head size moderately developed. Not the enormous wraparound eyes of a dragonfly, a predator that relies heavily on vision to track fast-moving aerial prey. Not the reduced vestigial eyes of a cave-dwelling or subterranean species that has abandoned visual input entirely. Somewhere in between eyes that worked, but were not the primary sensory instrument. This is consistent with the broader picture. An ant, living in a mid-Cretaceous forest floor or canopy environment, would have had access to light, but not the open, high-contrast visual environment that selects for extreme visual acuity. The forest would have been dappled, variable, full of visual noise. Chemical sensing through the antennae would have been more reliable for finding prey, for communicating with nestmates, for reading the environment. Vision for the hell ant was probably supplementary. Useful for detecting movement, useful for orientation in bright conditions, not the primary tool for hunting. This matters for the ambush versus pursuit question. A predator that hunts primarily by vision needs to see its prey to strike. A predator that hunts primarily by chemical sensing can strike at something it smelled before it saw. The hell ant trap, close range, precise, configured for a specific size, is more consistent with chemical detection than visual tracking. It found its prey by following its nose, then it killed by geometry. Under a scanning electron microscope, or its optical equivalent, applied through amber, the surface of the hell ant mandible is not smooth. It is textured. The specific texture varies across specimens and genera, but the general pattern is consistent. The outer surface of the mandible, the convex face, tends to be relatively smooth, the cuticle showing the fine microstructure typical of insect exoskeleton. The inner surface, the concave face that contacts prey, is different. It bears features. In some hell ant genera, the inner mandible surface is lined with fine denticles, small tooth-like projections that increase friction against a struggling prey item. Not large enough to cause major injury independently, but large enough to prevent a smooth surface from losing its grip on a soft, twisting body. The denticles are a retention mechanism. They are the difference between a trap that holds and a trap that slips. In Haidomyrmex specifically, the inner mandible surface shows features consistent with this general pattern, textured in a way that implies grip was part of the design priority. The tips show the fine, acute terminations already described. The middle section of the mandible curve shows the denticulation pattern. The presence of surface texture on the inner face and smoothness on the outer face is not random. It reflects the functional logic of the jaw. The outer surface does not contact prey, it moves through air. The inner surface contacts prey it must hold. Form follows function down to the microscale. What the microscope reveals in the end is not just anatomy, it is intention. The intention of a process evolution that does not intend anything but produces results so precise they look like craftsmanship. Not everything about the hell ant anatomy is settled. The clypeal horn, that downward projecting brace, presents a question that the amber frustratingly does not fully resolve. Insect cuticle is not uniformly rigid. Different regions of the exoskeleton vary in their mechanical properties. Some are hard and brittle, some are tough and somewhat elastic, some are genuinely flexible membranes. The ratio of hard to soft cuticle at any given point is determined by the proteins and chitin arrangement within it, and these molecular level details are not always recoverable from amber specimens. The question for the hell ant horn is functional. If the horn was fully rigid, a fixed brace, then the gap between horn tip and mandible tips was constant, and the trap was calibrated to a specific prey size range with limited tolerance. Prey too large wouldn't fit. Prey too small would slip through. A rigid horn implies a narrow target window. If the horn had some flexibility, if it could yield slightly under contact pressure, then the gap could accommodate a wider range of prey sizes. A flexible horn would function more like a spring-loaded catch than a fixed anvil. The trap would be more forgiving, more versatile, more applicable across a range of prey dimensions. Some researchers favor the rigid interpretation, citing the horn's apparent thickness and its position on the hardened frontal plate of the head. Others argue that the base of the horn, where it meets the clypeal plate, may have incorporated flexible cuticle, allowing limited compliance. This debate has not been resolved. It may not be resolvable with current imaging technology. And it matters because the answer tells us something about how narrow or broad the hell ant's ecological niche truly was. Small questions in amber science. Large consequences for understanding a life. The diversity within Haidomyrmex is one of its most scientifically valuable features and one of its most visually striking ones. Every genus in the tribe is a variation on the same theme, but the variations are wide enough to constitute their own catalogue of strangeness. Haidomyrmex, the horned ant, bears a clypeal horn that extends forward and upward in a dramatic arc, longer and more pronounced than the horn of Haidomyrmex, giving the face an almost heraldic quality. The mandibles in Haidomyrmex are among the most dramatically curved in the tribe. Haidomyrmex, the tongue ant, possesses a clypeal structure that is paddle-shaped rather than horn-like. Broad, flat, extended. The functional interpretation of this variant has generated considerable discussion. Is it a brace, like the standard horn? A surface that prey was pressed against? Something with a sensory function the standard model doesn't account for? Haidomyrmex carries mandibles that are less dramatically curved, but proportionally longer, reaching further ahead of the face, implying a slightly longer range strike geometry. Each genus in its variation tells us something about the design space of the hell ant trap. Some variations are interpretable. The longer horn of Haidomyrmex is consistent with larger prey or prey with a different body geometry. Others are less immediately obvious and honest. Researchers admit they are still working out what the variation means functionally. What is clear is that the tribe was not static. It diversified. It explored. Multiple lineages over millions of years were refining the same core innovation in different directions, each one a slightly different answer to the same question of how to catch a very specific kind of thing alive. The hell ant tribe is a laboratory that ran for tens of millions of years without a scientist in attendance, producing results that are only now being read. When a single core innovation, in this case the vertical axis trap, diversifies across multiple genera with different specific implementations, it tells us the core innovation was robust. It tells us there was enough ecological space around the basic design to support variation. Different horn shapes, different mandible lengths, different proportions, these are not random drift. They are adaptations. Each one was selected for, which means each one worked better than the alternatives in some specific context. This is evolutionary experimentation in the most literal sense. Not an experiment anyone designed, but a process of generating variation and filtering it through survival. The hell ants that survived long enough to leave fossils were the ones whose specific variant of the trap worked well enough to sustain a colony to produce reproductives to leave descendants. The variation also tells us the hell ant niche was not singular. If one specific prey type in one specific microhabitat were the only viable target, we would expect less variation, a strong convergence on a single optimal design. The actual variation suggests multiple viable prey types or multiple microhabitats or both. Different genera may have been filling slightly different ecological roles, each one a specialist within the broader specialization. This is in miniature the story of ant evolution generally. Ants do not succeed by being one thing. They succeed by being many versions of a few core ideas, by exploring the space around a viable design until they have filled every available niche. The hell ants did this within their tribe, within their time. They simply ran out of time before the exploration could continue. In 2020, a paper in the journal Current Biology described a specimen that changed the conversation about hell ant predation entirely. The specimen was a Haidomyrmex ellenbergeri, a hell ant genus with a particularly dramatic clypeal horn preserved in Burmese amber with prey in its jaws. Not near its jaws. In them, a nymph of an ancient cockroach relative, a small, soft-bodied insect of the order Blattodea held between the mandibles and the horn, its body pressed against the clypeal surface in exactly the position the trap geometry predicted. The specimen is, in scientific terms, extraordinary. It is direct behavioral evidence, not inferred, not reconstructed, not modeled, but photographed and described from physical reality. The trap was not hypothetical. The trap was real, and it worked on this. The prey's body is positioned with its dorsal surface, its back against the clypeal horn. The mandibles curve over and around the prey's ventral surface. The geometry is exactly what the biomechanical models predicted, which is to say the models were right, which is always a satisfying thing for science to discover about itself. The prey item, that cockroach nymph, was soft-bodied, consistent with every hypothesis about hell ant prey. Small, slow-moving relative to the predator, the kind of animal that in a forest full of things would not have seemed like a spectacular meal, but it was what the trap was built for, and the trap caught it. One frozen moment, 99 million years old, still held. The Haidomyrmex specimen proved the mechanism. It proved the horn was a functional brace, not an ornament. It proved hell ants hunted soft-bodied insects. It proved the trap geometry worked in the way the models said it would. These are not small proofs. They are the difference between a plausible hypothesis and a confirmed one. But a single specimen in a single posture is not a behavioral biography. What the amber caught was one moment, the moment of capture or just after. It did not catch the approach. It did not catch the strike. It did not catch what happened to the prey after capture, whether venom was delivered, whether the prey was consumed on the spot or carried back to a nest. It did not tell us about the nest. The colony structure of hell ants remains almost entirely unknown. Were they eusocial in the fully developed sense? Queen's workers, a division of reproductive labor. Were they in an earlier, less structured social arrangement? Did they have large colonies or small ones? Were the workers that hunted the same morphological caste as those that tended eggs? Or was there a division of labor already developed? The amber preserves individuals. It does not preserve societies. And ants are not individuals in any ecologically meaningful sense. An ant is a unit of a colony. What the colony was, how it was organized, how many of these trap-jawed hunters moved through the Cretaceous forest together. These questions remain entirely open. The frozen moment proved the trap. It left the life behind the trap untouched and unknown. Set aside everything familiar. Set aside the world as you have seen it, its geography, its weather, its colors, its sounds. The mid-Cretaceous Earth was not a different version of the present. It was a different planet running different systems under different rules. The continents were arranged differently. What is now North America was divided by a shallow inland sea, the Western Interior Seaway, running north to south through its center. South America and Africa had separated, but were still geologically young in their separation. India was an island moving north toward a collision with Asia that would not occur for another 40 million years. Antarctica was not frozen. Nothing was frozen. The poles were cool but vegetated, ice-free, inhabited. The atmosphere held more carbon dioxide than the present, significantly more by most estimates, producing a greenhouse effect that kept global temperatures considerably warmer. There were no permanent polar ice caps. Sea levels were higher. The ocean chemistry was different. The very baseline of what the planet's climate system did on a typical day was shifted. Into this world place a forest. Dense, humid, populated by plants that are not quite the plants of the present, by ferns and cycads and early flowering plants, just beginning to explore what they could become. Place insects in the forest canopy and the leaf litter. Place the hell ant among them, small, precise. Moving through a world that was fully formed and fully functioning, and utterly unlike anything alive today can access except through a piece of golden resin about the size of a marble. That is the world Haidomyrmex called home. Here is the detail that does the most to make the Cretaceous world feel genuinely alien. Not the different continents, not the warmer poles, not the different atmospheric chemistry. No grass. Grass, the family Poaceae, did not diversify into the dominant ground cover plant of open landscapes until after the Cretaceous ended. In the mid-Cretaceous, grasslands as we understand them did not exist. The open ground beneath the forest canopy was covered in ferns, mosses, and early flowering plants. The transition zones between forest and open areas were not meadows. They were fern prairies. This single fact cascades. Grasslands support grazers. Grazers support large predators. The whole ecological structure of modern savannas, prairies, and steppes, the food webs built on grass, did not exist. The animals that would evolve to exploit grasslands had not yet evolved because the grasslands hadn't evolved either. The forest floor where Haidomyrmex hunted was a fern floor. The ground beneath its feet, or rather beneath the tree bark it walked along, or the leaf litter it moved through, was a different texture entirely. A different chemistry. A different set of ecological relationships. For the hell ant, this probably mattered less directly than it mattered for larger animals. An ant hunting soft insect larvae in tree bark is not immediately affected by what covers the ground 20 meters below, but the whole biome that surrounded and supported its forest was organized differently, and that organization shaped what insects were present, what prey was available, and ultimately, what ecological role a small specialized predator could fill. The absence of grass is a reminder. The Cretaceous was not the present with different animals. It was a different operating system entirely. 99 million years ago, the flowering plants were doing something remarkable. They were winning. Not completely. Not yet. The mid-Cretaceous marks a transitional moment in plant history. The point at which angiosperms, the flowering plants, had diversified enough to begin displacing the older plant communities that had dominated terrestrial landscapes for hundreds of millions of years. Ferns, cycads, conifers, seed ferns, these were the incumbents. They had held their ecological positions through mass extinctions, through continental reorganizations, through ice ages and greenhouse episodes. They were not going to yield easily, and yet the angiosperms were spreading. Their reproductive innovation, the enclosed seed, the fruit, the flower, was proving enormously flexible. Flowers could attract pollinators, fruits could attract dispersers. The plant could, through these animal partnerships, extend its reach and its genetic diversity in ways that non-flowering plants could not match. The co-evolutionary experiment between flowering plants and insects was just beginning, and its consequences would ultimately reshape every terrestrial ecosystem on the planet. In the forest that produced the Burmese amber, both worlds coexisted. Ferns still covered the ground in dense ancient communities. Cycads raised their stiff fronds in the understory. But among them, early flowering plants were establishing footholds, experimenting with new flower forms, new fruit structures, new pollinator relationships. The hell ant lived in this transitional forest. It hunted in an ecosystem that was at the scale of millions of years in the process of becoming something else. The change was too slow for any individual ant to perceive, but it was happening, and eventually it would matter enormously. The specific trees that produced the resin preserved in Burmese amber have been a subject of ongoing investigation. Identifying a tree from its fossilized resin chemistry is possible. Different tree families produce resins with distinct molecular signatures, but the analysis is technically demanding and the results are not always unambiguous. The leading candidates are ancient relatives of the Araucariaceae, the family that today includes the monkey puzzle tree and the kauri. These are large resinous conifers capable of producing the quantities of resin necessary to create significant amber deposits. Modern kauri trees in New Zealand still produce resin in amounts large enough to form substantial deposits, and the kauri amber found in New Zealand is considered a useful modern analogue for understanding ancient amber-producing forests. The canopy of this forest would have been high and dense. Araucarian conifers are tall trees. Some living species reach heights comparable to a 10-story building, and a forest dominated by them would have been a closed canopy environment, the upper story forming a continuous ceiling over a shaded interior. Below that canopy, the light would have been filtered and dappled. The forest floor would have been humid, the kind of humidity produced by a dense tropical or subtropical forest, where the canopy intercepts rain and releases it slowly, where evapotranspiration keeps the air saturated, where everything that can grow on a surface does. Ferns on the ground, mosses on the bark, early flowering plants wherever a gap in the canopy let in enough light to establish them. The hell ant moved through this interior. The resin that preserved it ran from wounds in the bark of these tall ancient trees so old their lineage predates the dinosaurs, trees whose living relatives still stand in the southern hemisphere today, still producing resin, still not quite making amber. Resin is not passive. Trees do not produce it as a byproduct of some other process. They produce it deliberately in the sense that the capacity for resin production has been selected for, maintained, and refined over evolutionary time because it works. Resin seals wounds. When a bark beetle bores into a conifer trunk, the tree responds with a flood of resin, sticky, toxic to many organisms, physically filling the damage channel. The beetle, if it cannot escape, drowns or suffocates. The wound is sealed. The tree survives. This defensive resin flow is called pitch flooding, and it is one of the primary reasons large conifer trees can survive insect attacks that would kill smaller, less resine-productive trees. Resin also has antimicrobial properties. A sealed resin mass in a wound creates a hostile environment for fungi and bacteria. The secondary invaders that often kill trees after boring insects create entry points. The chemistry of the resin, its terpene compounds, its volatile components inhibits microbial growth in ways that plain physical sealing would not. None of this was done for science. The tree was not preserving anything. The resin that ran down the bark of that Cretaceous Araucarian catching a hell ant in mid-patrol was doing its ordinary defensive work, responding to damage, sealing a surface, protecting a living organism. The preservation was incidental. The ant was not the point. This is a fact worth holding for a moment. The amber that now sits in museum drawers around the world, holding some of the most scientifically valuable biological specimens in existence, was made by accident, by trees defending themselves, by chemistry doing what chemistry does. The archive was never intended. It simply happened the way most remarkable things happen without anyone meaning to. The landmass that would become Southeast Asia was in the mid-Cretaceous, positioned closer to the equator than it is today. The tectonic movements that would eventually carry various fragments of the region into their current positions had not yet fully played out. What would become Myanmar, Thailand, Indochina, these were parts of a complex, tectonically active zone where fragments of Gondwana were assembling against the southern margin of Asia. The climate of this region 99 million years ago was warm, significantly warmer than the present Southeast Asian climate, which is already tropical. Global average temperatures in the mid-Cretaceous are estimated to have been perhaps 8 to 10 degrees Celsius warmer than today's global average. In a region already near the equator, in a greenhouse world with no polar ice caps to moderate temperature extremes, the conditions would have been intensely humid and consistently hot. Rainfall would have been high and relatively constant, the kind of rainfall that supports closed canopy forest, that keeps leaf litter permanently moist, that produces the dense layered insect communities that amber so faithfully preserves. The wet conditions were also, of course, favorable for resin production. Moisture-stressed trees produce more resin in some circumstances, and a forest under constant biological pressure from insects and fungi would have been producing it continuously. For the hell ant, this climate was simply home. The heat, the humidity, the perpetual green, these were the conditions. Its physiology was calibrated to the conditions under which its trap had been refined over millions of generations. It was not surviving a difficult environment. It was thriving in the only environment it had ever known. The hell ant was not alone in the resin, not remotely. Burmese amber is among the most biologically diverse amber deposits ever studied, and the diversity is not merely taxonomic, it is ecological. The amber preserves not just the identities of organisms, but their relationships, their behaviors, their positions, in a web of interactions that operated 99 million years ago and has not operated since. Alongside the hell ants the amber preserves, flies hundreds of species representing lineages both recognizable and entirely extinct. Some are close to modern families, others are so different that placing them in the current classification system requires creating new categories for them. Beetles are present in remarkable variety, early representatives of groups that would go on to become the most species-rich order in the history of animal life. Moths and butterflies were in their infancy, early Lepidoptera, small and primitive, not yet the diverse pollinators they would become. Wasps are abundant parasitic wasps, in particular their ovipositors, sometimes still extended in the amber, frozen in the act of attacking a host. Springtails are present in the leaf litter inclusions, tiny ancient hexapods that have barely changed in 200 million years. Mites cling to larger insects. Pseudoscorpions wait in bark crevices. The community is dense. It is layered. It is a working ecosystem, preserved in cross-section, not a collection of isolated individuals, but a web of interdependencies, frozen mid-interaction held in gold. The hell ant moved through this community as a predator moves through any community, as a consumer of some of it, a competitor of some of it, prey to some of it. Not special in that sense, just another working part of a world that worked. Among the most scientifically arresting inclusions in Burmese amber are the parasitic wasps. Not because wasps are inherently dramatic, though some of them are, but because of what their presence and their anatomy tell us about the ecological complexity of the mid-Cretaceous forest. Parasitic wasps lay their eggs in or on the bodies of other insects. The larva hatches and consumes the host from within a strategy so effective it has been independently invented by dozens of wasp lineages across evolutionary history. The diversity of parasitic wasps today is staggering. There are parasitic wasps that target caterpillars, wasps that target beetles, wasps that target fly pupae, wasps that target spider egg sacs, and wasps that parasitize other parasitic wasps. In the Burmese amber, parasitic wasps are present in an already remarkable variety. Not primitive, barely differentiated early forms, actual specialists. Wasps with ovipositors adapted for specific host types, specific host locations, specific host developmental stages. The amber preserves some of these ovipositors in extraordinary detail. Slender, multi-articulated probes that could navigate bark, penetrate plant tissue, or reach into the chambers of wood-boring beetle larvae. This specialization tells us something important about the mid-Cretaceous forest. A parasitic wasp that is specialized for a specific host type requires that host to be reliably present. Specialization implies abundance. The ecological community in that forest was not thin or impoverished. It was dense, layered, with enough consistent prey populations to support not just predators, but specialized predators and specialized parasites of those prey. The hell ant hunted in a forest teeming with life, so teeming that it could support not just its own specialized trap, but an entire community of specialists, each one calibrated to something else. If you want a measure of deep time, consider the cockroach. Cockroaches as a recognizable group appear in the fossil record more than 300 million years ago, before the dinosaurs, before the first mammals, before the first flowering plants, before a significant fraction of the history of animal life on land had even begun. The basic cockroach body plan, flat oval, with long antennae and a characteristic scutellum shielding, the thorax was already established before the Permian period ended in the largest mass extinction Earth has ever experienced. The cockroach survived that extinction. It survived the one at the end of the Triassic. It has been present, recognizable, and functionally successful through every major reorganization of life on land. The cockroaches in Burmese amber are not identical to modern cockroaches. The mid-Cretaceous fauna included forms with external ovipositors, a feature the ancestors of modern cockroaches had, but modern species have lost, and some had proportions and wing geometries that don't match anything living today. They were Cretaceous cockroaches, different species assemblages, occupying slightly different ecological roles, but they were recognizable. Hold a piece of Burmese amber with a cockroach inclusion, and you will know immediately what you are looking at. The shape, the antennae, the general body geometry, these are not ambiguous. The cockroach nymph in the Haidomyrmex specimen, the prey item that proved the hell ant trap, was one of these ancient relatives. Soft-bodied in its nymph stage, slow-moving, present in the forest litter and on bark surfaces where hell ants patrolled. It was in the context of the Cretaceous community ordinary prey. Unremarkable. The kind of small, soft insect that keeps predators fed. It happened to be the one that was caught at the wrong moment, the one that became evidence. The amber's record extends beyond insects. Occasionally, not commonly but memorably, Burmese amber preserves fragments of larger organisms. A feathered dinosaur tail section described in 2016 provided direct evidence of Cretaceous feather structure in 3 dimensions. Portions of ancient bird wings, fragments of frogs, a gecko-like lizard, or rather the shed skin of one, the scales preserved in the amber matrix, with the same fidelity given to insects 1/10 of its size. These larger inclusions are exceptional. The physics of amber entrapment favor small organisms. Something the size of an insect can be overwhelmed by a resin flow quickly enough to be preserved before it escapes. Larger animals typically struggle free, or the resin mass is not sufficient to fully engulf them. What gets preserved from larger organisms tends to be fragments, a tail, a wingtip, a patch of skin rather than complete animals. The lizard scales are worth dwelling on. Scales are not the most informative part of a reptile. They tell you less about the animal's ecology than its skeleton would, less about its phylogenetic position than its skull. But they are there. They are real. They are the surface of a living animal that moved through the same forest as Haidomyrmex on the same bark surfaces at roughly the same time. The lizard that shed those scales or was partially caught by the resin was probably insectivorous. Most small Cretaceous lizards were. It may have eaten insects similar to the ones the hell ant hunted. It may have eaten hell ants. The amber does not tell us. It gives us the scales and withholds the biography the same way it gives us the hell ant's posture and withholds its colony. What we have is proximity. Different organisms, different sizes, the same tree, the same moment. A forest glimpsed. The land beneath the Hukong Valley today sits at roughly 26 degrees north latitude, subtropical mountainous, the southern edge of the Himalayan foothills. But latitude is not a fixed property of land. Tectonic plates move, continents drift. A location that is subtropical today may have been equatorial in the past, or polar or underwater. 99 million years ago, the landmass that would become northern Myanmar was part of a complex tectonic situation involving fragments of ancient Gondwana, the southern supercontinent that were migrating northward toward the Eurasian plate. Reconstructions of mid-Cretaceous paleogeography place this region significantly closer to the equator than it sits today, perhaps at 10 to 15 degrees north, well within the tropical belt. This matters for understanding the forest. A tropical forest at 10 degrees north in a mid-Cretaceous greenhouse world would have been among the most productive terrestrial ecosystems on the planet. High rainfall, high temperatures, continuous growing season, enormous biomass. Production. The density of insect life preserved in the amber is consistent with exactly this kind of environment. It also means the forest that produced the amber no longer exists anywhere in the physical sense, not just because the trees are gone and the organisms are gone, but because the ground it stood on has moved. The soil, the bedrock, the entire geological substrate of that forest has traveled thousands of kilometers over 99 million years, tilting and compressing as the Indian subcontinent crashed into Asia and threw up the Himalayas, carrying the amber with it to a latitude and altitude the forest it came from never occupied. The amber is a traveler. It began in a tropical forest near the equator. It ended in a subtropical mountain valley. The journey took almost 100 million years. Continental drift operates on timescales that make human history feel instantaneous. The plates move at roughly the speed fingernails grow a few centimeters per year, but over millions of years, those centimeters accumulate into thousands of kilometers of displacement. Mountain ranges rise. Ocean basins open and close. Land masses that were once connected separate into isolated evolutionary theaters, and land masses that were once isolated collide, mixing their faunas in sometimes catastrophic ways. In the mid-Cretaceous, the arrangement of continents was dramatically different from today. The Atlantic Ocean existed but was narrower, a young ocean still expanding. The Tethys Sea, a vast tropical ocean that no longer exists in any recognizable form, separated the northern land masses from the southern ones, its warm, shallow waters hosting an extraordinary marine fauna. India, as noted, was an island continent, having rifted away from Gondwana and begun its long northward journey. The fragment that carried the amber forest was in the mid-Cretaceous, an island or near-island landmass, geologically complex, tectonically active, positioned in the warm Tethyan tropics. Its isolation, if it was isolated, would have had evolutionary consequences. Island faunas develop their own character, their own endemic lineages, their own ecological structures. Whether the hell ant fauna was endemic to this region or was part of a broader Cretaceous ant fauna distributed across multiple land masses is a question the distribution of specimens makes difficult to answer definitively. Hell ant genera have been found in amber from other deposits. French amber, Canadian amber, suggesting the group was not restricted to the Burmese region. The trapjaw strategy was not a local invention. It was a global one, playing out across the Cretaceous world in multiple forests on multiple continents in multiple variations. The specific amber forest was local. The hell ant idea was not. The existence of a rich amber deposit in northern Myanmar is not just a lucky accident of preservation. It is a data point in a larger map, a map of where tropical and subtropical forests existed in the mid-Cretaceous, and how those forests were distributed across a planet arranged differently from the one we inhabit. Amber deposits require specific conditions to form. First, a resin-producing forest. Not all forests produce resin in amber-forming quantities. Second, a depositional environment that can bury the resin quickly enough to prevent oxidation and biodegradation, typically a river delta, a coastal plain, or a low-lying basin where sediment accumulates rapidly. Third, the right subsequent geology burial deep enough for polymerization, but not so deep that heat destroys the organic structure. The Burmese amber deposit satisfies all of these conditions, and its existence tells us that a large, productive resin-generating forest was present in this region 99 million years ago. The size of the deposit suggests the forest was extensive and long-lasting, not a temporary patch but a sustained ecosystem covering a significant area. Comparing the Burmese amber deposit with other Cretaceous amber deposits worldwide, French amber, Lebanese amber, Canadian amber, Siberian amber, researchers can begin to sketch the distribution of Cretaceous forests. The picture that emerges is of a world with extensive tropical and subtropical forest cover at latitudes that today are temperate or even subarctic. The mid-Cretaceous greenhouse pushed forest belts poleward-filled regions that today are deserts with dense vegetation and created a planet far more uniformly forested than the present. The hell ant lived not in an exceptional forest. It lived in one node of a vast planet-spanning green system, a system so extensive and so productive that it supported ecological specialization at the scale of a single ant's jaw geometry. Walk into any garden today and disturb the soil. Within seconds, ants will appear, and depending on your location, those ants will belong to one of a handful of highly successful subfamilies: Myrmicinae, Formicinae, Dolichoderinae. These three subfamilies alone account for the majority of living ant species and the overwhelming majority of ant ecological biomass on Earth. They are the ants, the ones we know, the ones that farm aphids and cut leaves and build mounds and form supercolonies. In the mid-Cretaceous, none of these subfamilies dominated. Most of them barely existed. The ant fauna of 99 million years ago was ecologically thin by modern standards. Ants were a new group recently diversified from wasp, ancestors still occupying a relatively minor role in terrestrial ecosystems. The modern ant dominance, the point at which ants became the most ecologically significant group of terrestrial invertebrates by biomass, came later, much later. It was built on the angiosperm revolution, on the spread of grasslands, on ecological opportunities that the mid-Cretaceous world had not yet generated. In the amber fauna, ants are present but not dominant. They share the fossil record with a wasp fauna far more diverse and ecologically prominent than anything that exists today. The wasps were still the ruling Hymenoptera. The ants were newcomers, experimenting, diversifying, trying out designs. Hell ants were one of those experiments. An early, ambitious, highly specialized attempt to carve out a predatory niche in a world where the ecological space for specialized ant predators had not yet been thoroughly claimed. They were ahead of their time, in a sense, a sophisticated solution to a problem that the ant lineage as a whole was still in the early stages of addressing. The oldest confirmed ant fossils predate the Burmese amber by perhaps 20 to 30 million years, pushing the origin of ants back toward the early Cretaceous, or possibly the late Jurassic. These earliest ants are known from very few specimens, and their morphology is in some ways more wasp-like than ant-like. The boundaries between the ant lineage and its wasp ancestors are blurred in the earliest fossils, the diagnostic features of ants only gradually assembling into the combination we recognize. By the time of the Burmese amber ants had been diversifying for tens of millions of years. The fauna represented in the deposit includes both stem group ants, early lineages that branched off before the modern subfamilies diverged, and some of the earliest representatives of groups that would go on to become dominant. The hell ants belong firmly to the stem group. They are not ancestral to any living ant. They are a branch that grew in its own direction for millions of years, elaborated an extraordinary predatory system, and then stopped. The stem group ants of the mid-Cretaceous were in general more predatory than their modern descendants. The transition from a predatory lifestyle to the ecological generalism that characterizes most modern ants, the seed-collecting, fungus farming, aphid herding, omnivorous flexibility, came later, driven in part by the ecological farming opportunities created by flowering plants. The earliest ants were hunters. The hell ants were the most specialized hunters among them. In a world of early hunters, they were the most committed, the ones who had gone furthest in a single direction, the ones for whom hunting was not an option but an architecture. Ecology is not static. The roles that organisms play in ecosystems are not fixed properties of the organisms themselves. They are positions in a web of interactions, and those positions shift as the web changes. An organism that is a minor player in one geological period can become a dominant one in the next, given the right combination of ecological opportunity and evolutionary luck. Ants today are among the most ecologically significant organisms on Earth. By some estimates, ants constitute somewhere between 15 and 25% of terrestrial animal biomass, a figure that requires a moment to absorb. Every ant colony, every worker, every queen, every larva, all added together across every species on every continent, represents a mass of living material that dwarfs the combined mass of all wild mammals. Ants move more soil than earthworms in some ecosystems. They disperse more seeds than any other group of animals in certain forest types. They are, in the most literal sense, engineers of the terrestrial world. None of this was true in the mid-Cretaceous. The ants of 99 million years ago were ecologically minor. They were present in forest communities, filling small predatory and scavenging niches, but they had not yet achieved the dominance that would later make them planetary forces. The web of interactions that would eventually center on ants, the aphid farming, the seed dispersal, the fungal agriculture had not yet formed. The hell ant lived in this early, tentative chapter of ant ecological history. It was an experimenter in a lineage of experimenters. It found a niche, a specific, precise, effective niche, and occupied it fully. The niche ended, but the lineage that eventually replaced it built a world. The amber did not preserve itself. It needed help from geology, the slow, impersonal processes of sediment, accumulation, and burial that transform surface materials into the subsurface record. When resin falls from a tree as droplets as larger masses as the accumulated flow from a wound over weeks or months, it lands on the forest floor. There it begins its transformation almost immediately. Volatile compounds evaporate. The surface oxidizes, developing a skin. Microbial activity begins to attack the organic material. Under normal circumstances, the resin would be gone within years, consumed, degraded, returned to the soil carbon cycle. Preservation requires burial. The amber deposits of the Hukong Valley were created by a specific geological context, a sedimentary basin where river-transported sediment accumulated rapidly enough to bury resin masses before degradation could complete. The sediment, fine-grained, oxygen poor in its deeper layers, created the anoxic conditions that slow microbial activity and allow polymerization to proceed. Over millions of years, the sediment above the amber accumulated, compacted, and lithified into the sedimentary rock that now overlies the deposit. The pressure of that accumulation, thousands of meters of rock, eventually over tens of millions of years, contributed to the amber's hardening and the completion of its polymerization. Then tectonic forces lifted the deposit. Erosion stripped away some of the overlying rock. The amber approached the surface again, not quite where it started, not quite what it was when it began, but intact, still holding what it caught, still waiting to be found by something with the tools to understand it. Geology gave it time, chemistry gave it fidelity, erosion gave it back. 100 years is within the range of a single human memory. Not your memory, but someone alive today could in principle have been alive 100 years ago. The events of a century past are accessible through living testimony, through recorded voices, through photographs taken by people still remembered, by people still living. 100 years is history. It is also, in some residual sense, almost present. 1,000,000 years is beyond all of that. 1,000,000 years ago, the species that would become humans was still assembling itself in Africa. Language did not exist. Fire was new. Every human institution, every city, every name, every idea, none of it had happened yet. 1,000,000 years is a different world fully. 100 million years is 100 of those. Stack 100 different worlds, each one as remote from us as the African grasslands of 1,000,000 years ago, and you approach the distance to the hell ant. The forest it lived in has been replaced many times over by different forests, then by different landscapes, then by the current geography, which is itself temporary, a snapshot in a process that will continue long after the current arrangement is gone. The amber holds a moment from that depth, a single morning or night or afternoon from 100 million years ago. The ant was doing something. The resin fell. The moment was caught. There is no human framework for the number. There is only the amber warm in your hand light as wood carrying a frozen posture from an inconceivable distance. The number is too large to feel. The amber is small enough to hold. That is the whole of the wonder contained in something the size of a grape. The Burmese amber does not preserve a random sampling of Cretaceous life. It preserves with remarkable specificity the organisms that lived in and around a particular kind of forest at a particular moment in geological time in a particular region of the ancient world. It is a snapshot highly detailed within its frame, but bounded by the frame. Within that frame, the diversity is extraordinary. Researchers studying Burmese amber have described thousands of species, new to science, new genera, new families, in some cases new orders. The deposit has been yielding new discoveries continuously since systematic study began in earnest in the late 20th century, and the rate of new species description has not slowed appreciably. Among the organisms sharing the amber, with Haidomyrmex ancient flies, whose wing venation matches no living family. Beetles that represent extinct lineages with no modern descendants. Parasitic wasps with ovipositor morphologies unlike anything in the current fauna. Early moths with wing scales preserved in such detail that their optical properties, whether they were iridescent, whether they reflected ultraviolet, can be analyzed. Spiders in the middle of building webs. A harvestman recognizable immediately, despite its 99 million years. Pseudoscorpions clinging to the legs of larger insects, hitchhiking a behavior called foracy that those lineages still practice today. The snapshot is a community, not just a list of species, but a web organisms in relationship organisms in behavior organisms caught in the acts that define their lives. The hell ant is one thread in that web. Remove it and the web is thinner. But the web was there regardless. Full, dense, functional, and entirely gone. There is a specific quality to the strangeness of Burmese amber that accumulates as you learn more about it. It is not a single surprising fact. It is a series of them layering on one another, each one adding to a weight that becomes eventually something close to vertigo. The forest is gone. Not just the individual trees, the entire forest type, the ecological community, the specific assemblage of organisms that produced and inhabited that amber. It does not exist anywhere on Earth. There is no living analogue, no modern forest that replicates the specific combination of Araucarian conifers, fern, ground cover, early angiosperms, Cretaceous insect fauna, and warm tropical climate. The closest living approximations, kauri forests in New Zealand, tropical rainforests in the Indo-Pacific, share some features and none of the whole. The continent it stood on has moved. The climate that sustained it has changed. The evolutionary lineages it harbored have mostly ended. The prey the hell ant hunted is unidentified. The colony structure of the hell ant is unknown. The total duration of the hell ant lineage, how many millions of years it existed before the amber moment and after, is only approximately known. What the amber gives is a moment. Precise, physical, irreplaceable. What it withholds is everything that moment was embedded in the before, the after, the context that would make the moment fully legible. Holding that amber, knowing all of this produces something that is not quite grief and not quite wonder. It is the feeling of standing at the edge of something that goes down further than you can see. The amber is the edge. Everything below it is time. Amber's preservative power is chemical before it is anything else. Understanding why the hell ant looks the way it does, why the surface detail is present, why the posture is intact, why the amber specimen is more informative than a stone fossil of comparable age, requires understanding what happened to the resin over 99 million years. Fresh resin is a complex mixture of organic compounds. Terpenoids, large hydrocarbon molecules, form the bulk of it. Volatile monoterpenes give fresh resin its sharp, distinctive smell. They evaporate quickly after the resin is exposed to air. What remains are the heavier diterpenes and sesquiterpenes, which begin to cross-link, forming chemical bonds between adjacent molecules, gradually building a denser, harder polymer network. This cross-linking is polymerization. It proceeds slowly at surface temperatures, faster under burial conditions where heat and pressure accelerate the process. Over millions of years, the polymer network becomes increasingly dense and increasingly stable. The volatile components are lost entirely. The remaining material is a solid, organic polymer, resistant to water, resistant to many acids, resistant to most microbial degradation. Amber. The biological material trapped within is protected by the amber matrix in two ways. Physically, the resin encases the organism completely, excluding oxygen and water, the two primary agents of biological decay. Chemically, the terpene compounds in fresh resin are antimicrobial, toxic to the bacteria and fungi that would otherwise consume soft tissue within days. The result is preservation of a quality that stone fossils cannot match. The hell ant in amber has its original three-dimensional form. Its cuticle surface is the original surface. Its posture is the posture it died in. Nothing has been compressed, mineralized, or replaced. It is not a cast. It is the thing itself held. The difference between amber preservation and stone preservation is the difference between a pressed flower and a flower suspended in glass. Both preserve the flower. Only one preserves it as it was. Stone fossils form through replacement. The original organic material is gradually dissolved and replaced by minerals or compressed into a thin film of carbon or preserved as an impression in the surrounding rock. The result is often extraordinarily informative bone structure, shell form, skin impressions, even soft tissue outlines in exceptional cases. But the original material is gone. What remains is a mineral replica, however faithful. Amber preservation retains the original material. The cuticle of the hell ant, that thin, rigid outer covering of chitin and protein, is the actual cuticle. Not a mineralized replica. Not an impression. The original surface with its original texture, its original microstructure, the actual molecular architecture of an insect that lived in the Cretaceous. This has practical scientific consequences. Researchers using scanning electron microscopy on amber inclusions can examine surface features at magnifications. Impossible on stone fossils, the fine denticles on a mandible's inner surface, the texture of an eye's facets, the microstructure of a wing membrane. These details are not just visually impressive, they are functionally informative. Surface texture tells you about function. Function tells you about behavior. Behavior tells you about ecology. Amber also preserves posture, as discussed, and occasionally preserves behavioral interactions. The Haidomyrmex predation specimen is an example of behavioral preservation impossible in stone. Stone records presence. Amber records moment. For the hell ant, this distinction is the difference between knowing an animal existed and beginning to understand what its life was like. Stone would have given the first. Amber remarkably gives something closer to the second. Amber is not a perfect archive. It is extraordinary, genuinely, almost unreasonably extraordinary in what it holds, but it has limits, and those limits are as important to understand as its capabilities. The first limit is selectivity. Amber preserves what the resin caught, and the resin caught what was near the wound site when it flowed. The organisms trapped in amber are not a random sample of the Cretaceous fauna. They are a sample of the organisms that were present on or near tree surfaces, bark-dwelling insects, canopy inhabitants. Anything that had the misfortune to walk across a resin flow at the wrong moment. Soil-dwelling organisms, aquatic organisms, open-ground organisms, these are underrepresented or absent. The hell ant's colony, presumably nesting somewhere, is not preserved because colonies are underground or in enclosed wood away from resin flows. The second limit is chemical. While amber preserves the three-dimensional form and surface structure of inclusions with extraordinary fidelity, it does not preserve everything at the molecular level. Soft internal tissues, muscles, organs, the contents of the digestive tract are typically lost. What remains after millions of years is the cuticle, the hardened external skeleton, and sometimes a thin residue where soft tissue was. The internal anatomy of the hell ant, its musculature, its venom glands, its brain structure, is inferred, not observed. The third limit is interpretive. Amber shows posture, surface, detail, and occasionally behavior. It does not show lifespan, growth stages, seasonal behavior, social interactions, or the countless other dimensions of a life that only sustained observation over time can reveal. The hell ant in amber is a still image from an unknowable film. Extraordinarily detailed, deeply informative, and, in all the ways that matter most for understanding a life permanently incomplete. Science works with what it has. What amber has is remarkable. What amber withholds remains its own. In 1993, a film introduced the world to the idea that ancient DNA preserved in amber could be used to resurrect extinct organisms. The premise was vivid, the execution was entertaining, and the science it was based on was at the time being actively investigated by real researchers who had reported finding DNA fragments in amber-preserved insects. The popular version of the story ends there with the exciting possibility. The scientific version continues, and it goes in a different direction. Subsequent research thoroughly failed to replicate the early DNA extraction claims from amber. The fragments initially reported were almost certainly contamination modern DNA from the researchers themselves, from bacteria from environmental sources mistakenly amplified alongside or instead of any genuine ancient signal. The conditions inside amber, while extraordinary for preserving structure, are not sufficient to prevent DNA degradation over geological timescales. DNA is an unstable molecule. Even under ideal conditions, it breaks down and becomes unreadable within a few 100,000 years, possibly up to 1 million under exceptional circumstances, but not 99 million. Not remotely. The scientific consensus now firmly established is that genuine ancient DNA from amber inclusions is not recoverable. The organisms in Burmese amber are structurally preserved but molecularly degraded, at least at the nucleic acid level. What amber holds is form. What it cannot hold is sequence. For the hell ant, this means there will be no genome, no molecular phylogenetics from the specimens themselves. The evolutionary relationships of Haidomyrmex must be worked out from anatomy, from the shape of the jaw, the structure of the head, the proportions of the body, using morphological methods that are powerful but carry their own uncertainties. The amber holds the body. The instructions that built the body are gone. The specimens attributable to Haidomyrmex specifically, as opposed to the broader hell ant tribe, are few, and each one is a different window into the same animal. Some specimens preserve the head in exceptional detail, the mandible geometry clear, the clypeal horn unambiguous, the eye facets visible under magnification. These are the specimens that established the anatomical diagnosis of the genus. They are the ones reproduced in publications, the ones used to build biomechanical models, the ones that defined what Haidomyrmex is. Other specimens preserve the body more completely, but with the head partially obscured by bubbles in the amber matrix or by the amber's own internal fractures, cracks that developed over millions of years as the material settled and shifted. These specimens are less useful for anatomy, but more informative about body proportions, leg structure, and the overall gestalt of the animal. Some specimens are fragmentary, a head without a body, or a body without a complete head preserved, when the resin caught only part of an animal that escaped or was partially consumed before entrapment. Fragments are still valuable. A fragment preserves what it preserves, and partial information is better than no information as long as its partiality is acknowledged. What no complete Haidomyrmex specimen yet shows is the ventral surface of the head in unobstructed detail, the underside where the mouth parts attach, where the labial and maxillary palps are positioned. The feeding apparatus below the mandibles is ironically one of the least well-characterized parts of the animal, obscured by the amber matrix in most specimens, or by the orientation in which the ant was trapped. How the hell ant actually consumed prey once it was caught remains partially hidden. The trap is visible. What came after the trap is not. In taxonomy, every species is anchored by a single specimen, the holotype. This is the physical object against which all other specimens are compared. When a researcher wants to know whether a new fossil belongs to Haidomyrmex scimitarus, they compare it directly or through published descriptions and images to the holotype. The holotype is the definition made physical. The holotype of Haidomyrmex scimitarus, the type species of the genus, the specimen from which the original description was written, is a piece of Burmese amber containing a single well-preserved worker. It is the specimen that Rasnitsin and Dlusky worked from in their 2003 description. It resides in an institutional collection, accessible to researchers through established protocols. Holotypes carry a weight beyond their physical size. They are the fixed points of biological nomenclature, the anchors that prevent taxonomic drift, that ensure the name means the same thing in a paper written today as it meant in a paper written 20 years ago. If the holotype is lost, the name becomes unstable, still valid, still in use, but no longer attached to a physical reference. This is why holotypes are kept in institutional collections rather than private hands, why they are subject to special protocols for access and loan, why their location and condition are tracked. The hell ant holotype is small enough to hold between 2 fingers. It is in physical terms one of the least imposing objects in whatever drawer it occupies. In scientific terms, it is irreplaceable, the original definition of a genus that existed for tens of millions of years, hunted with geometry. No living ant has replicated and left the world before anything existed that could remember it. One piece of amber, one specimen, the entire official identity of a genus resting there. The name scimitarus is not accidental. A scimitar, the curved single-edged blade of ancient Middle Eastern and Central Asian tradition, is precisely the shape the mandibles recall. Rasnitsin and Dlusky chose the epithet deliberately, and it is one of those rare cases where a species name is both scientifically informative and visually exact. The holotype preserves the defining features of the genus in sufficient detail to establish the diagnosis. The mandibles are the central feature, their curvature, their length relative to the head, the angle at which they attach to the head capsule. In the holotype, the mandibles are visible in a lateral or oblique view that shows the upward arc, clearly the scimitar geometry that gave the species its name. The clipial horn is present and visible, though the exact tip detail is partially obscured in some viewing angles by the amber matrix. Its position projecting downward from the clipeal plate toward the space below the mandibles is clear enough to establish the functional relationship between horn and jaw. The head proportions, the forward tilt, the relative size of the head compared to the thorax, the position of the eyes, are all readable from the holotype. The petiole is visible, its narrow, defined form consistent with the ant body plan. The gaster, the antennae present identifiable, informative. What the holotype does not show is the full 3-dimensional geometry of the mandibles. It is an amber specimen viewable from multiple angles but constrained by the matrix. Subsequent specimens and the application of micro-CT scanning to hell ant material generally have extended the three-dimensional picture that the holotype alone could not provide. The holotype opened the door. Everything since has been walking through it. The cuticle is the face the amber shows. Behind the cuticle, inside the amber-preserved exoskeleton, the soft anatomy is largely gone, replaced over millions of years by the amber matrix itself, or by a thin residue that does not yield useful structural information. But inference is not nothing. The external anatomy of insects is tightly coupled to the internal anatomy. The shape of the exoskeleton reflects the shape of the structures it houses, and the positions of muscle attachment scars on the inside of the cuticle record where the muscles were how large they were, and in some cases how they were oriented. For the hell ant, the most important internal anatomy question concerns the mandible muscles. The muscles that close the mandibles, the adductors, and the muscles that open them, the abductors, are housed in the head capsule and attached to the mandible base. The size of the attachment scars visible on the inner surface of the head capsule in well-preserved specimens or micro-CT scans gives an estimate of muscle cross-section, which gives an estimate of force output. The venom glands are another inferential target. Most ant workers possess venom glands evolved from the same ancestral structures as wasp stingers, and the presence of a well-developed petiole in Haidomyrmex is consistent with a functional venom system. But direct evidence of the venom gland structure is not available from amber specimens. Fast-acting or slow, delivered by sting or by bite, these questions touch the invisible interior that amber cannot reach. The nervous system, the circulatory system, the digestive tract gone. The brain that processed the chemical signals from those forward-directed antennae and translated them into the precise geometry of a hunt gone. Present once for millions of years in every individual of every hell ant colony that ever existed, now entirely absent except in the inferences careful anatomy allows. Placing an extinct organism in a family tree is not a simple act. It requires identifying the features that reflect genuine evolutionary history, shared ancestry, and distinguishing them from features that reflect convergent evolution, parallel evolution, or simple ancestral retention. In insects and in ants specifically, this distinction is perpetually demanding. When Rosnitsin and Lusky described Haidomyrmex in 2003, they placed the hell ants in the subfamily Scythes, a group of early wasp-like ants from Cretaceous amber that had been established in the 1960s from New Jersey amber specimens. The Scythes were understood at the time as the most primitive known ants, the closest fossil relatives to the wasp ancestor from which ants evolved. This placement was reasonable given the available evidence. Hell ants share certain features with Scythes ants, features that appear primitive, retained from the ancestral condition. But it was not universally accepted, and subsequent researchers with access to more specimens and more sophisticated analytical methods found the placement unsatisfying. The problem was that hell ants also have highly derived features that are clearly the product of significant evolutionary modification, not retention of the ancestral condition. The upward curving mandibles and the clipeal horn are not primitive. They are specialized. An ant with very primitive overall body plan and very derived predatory apparatus is a taxonomic puzzle. Where do the derived features come from, and how do you weight them against the primitive ones? The debates over hell ant placement in the ant family tree persisted through the 2010s, with different research groups producing different analyses and reaching different conclusions. The disagreement was not about whether hell ants were ants that was never in doubt. It was about where specifically they fit within the ant lineage's own early diversification. The tribe Haidomyrmex was established to give the hell ants their own formal home, a taxonomic container that acknowledged both their distinctiveness and their internal coherence. A tribe sits between the subfamily level and the genus level in taxonomic hierarchy, grouping genera that share a common ancestor and a suite of shared derived features. The shared derived features of Haidomyrmex are primarily the trap apparatus, the upward curving mandibles, and the clipeal modification that creates the counterbrace. These are the synapomorphies in technical language, the shared derived characters that define the group and distinguish it from other ant lineages. Within the tribe, the genera currently recognized include Haidomyrmex, Ceratomyrmex, Linguamyrmex, Haidomyrmex, 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 and several others whose status is still being debated in the literature as new specimens, emerge. The number has grown since the tribe was first established, and will likely continue to grow as amber collections are more thoroughly examined and as new material enters the scientific domain. The tribe is currently placed within the subfamily Scythes by some researchers and given its own subfamily status, Haidomyrmecinae, by others. This disagreement reflects unresolved questions about the tribe's relationships to other Cretaceous ant lineages, and it matters more than it might appear. Subfamilial placement is a statement about evolutionary history, about which lineages are most closely related to which, about the sequence of branching events that produced the modern ant fauna. The hell ants have their name, their tribe, their genera. What they do not yet have in the fullest sense is their place in the story of ant evolution, their exact position in the sequence of events that led from the first ant to the 14,000 species alive today. That position is still being worked out carefully and contentiously from a handful of amber windows. Phylogenetics, the science of reconstructing evolutionary relationships, makes a fundamental distinction between stem groups and crown groups. The crown group of any lineage consists of all living members of that lineage plus their last common ancestor. The stem group consists of all extinct lineages that branched off before that last common ancestor lineages that are related to the crown group but are not part of it. Evolutionary experiments that preceded the modern configuration. For ants, the crown group is all living ant species, the 14,000 plus described species plus their last common ancestor. The stem group consists of all the extinct ant lineages that diverged before the radiation that produced the modern fauna. The Cretaceous ants whose descendants did not survive into the present, hell ants, are stem ants. This is not a contested conclusion. It follows from the simple fact that no living ant is descended from Haidomyrmecinae. The tribe went extinct. Its lineage ended. Whatever evolutionary experiments it represented were not carried forward into the modern fauna. What is debated is where in the stem the hell ants sit. Are they very early, branching off near the base of the ant family tree before most of the major lineages diverged? Or are they later, a more derived branch of the stem group more closely related to some crown ant subfamilies than to others? The answer has implications for understanding ant evolution. An early branch position would suggest that the trap jaw strategy was among the very first specialized predatory experiments in ant history. A later position would suggest that the strategy evolved within an already diversified ant fauna, that the hell ants were a secondary experiment, not a primary one. Current analyses suggest a relatively early stem position, but the confidence intervals on that conclusion are wide and different analytical methods produce different results. Scientists still debate whether hell ants represent an early independent experiment in ant predation or something more derived. The question is open. The amber, as always, keeps its own counsel. When molecular data is available, when DNA can be extracted from specimens, and sequenced evolutionary biologists can use the molecular clock. The principle is straightforward. DNA accumulates mutations at roughly predictable rates. By counting the differences between the DNA sequences of two related species and calibrating the mutation rate against fossil dates, researchers can estimate when those two species last shared a common ancestor. The hell ant has no recoverable DNA. The molecular clock is unavailable. This forces researchers back to morphological methods, comparing physical features across taxa to infer relationships and indirectly divergence timing. Morphological analysis can identify which features are shared and derived the synapomorphies that indicate common ancestry and can produce a branching diagram, a cladogram that represents the inferred evolutionary history. Combined with the geological dates of the amber deposits in which specimens are found, this produces approximate divergence estimates. But morphological phylogenetics has its own uncertainties. Features that look similar can have evolved independently. Convergence, the bane of morphological analysis, creates false signals of relationship. Features that look different can have evolved from a common ancestral state through two different pathways, parallel evolution, equally misleading. The training and judgment of the researcher matters enormously, which introduces a human variable that molecular methods partially bypass. For hell ants, the morphological analyses consistently support an early Cretaceous or possibly late Jurassic origin for the ant lineage as a whole, with the Haidomyrmex diverging sometime in the early to mid-Cretaceous. But the precise timing when the hell ant lineage branched, how long it persisted when the last hell ant died, remains approximate. The amber gives the moment of preservation. It does not give the duration of the life before it. Morphological cladistics is at its core a sorting problem. You have a set of organisms. Each one has a set of physical features, characters in the technical language. Some of those features are ancestral, present in the common ancestor of the group, retained without modification. Some are derived, modified from the ancestral state in one or more lineages. Shared among some lineages and absent in others are the signal. They indicate common ancestry. They are the evidence from which a family tree is built. The process applied to hell ants involves assembling a character matrix. Dozens or hundreds of features, the angle of the mandible attachment, the proportions of the head, the number of antennal segments, the structure of the petiole, the shape of the gaster, scored for each specimen and each comparative taxon. Living ants, other extinct ants outgroups. The matrix is fed into analytical software that searches for the most parsimonious branching arrangement, the tree, that requires the fewest evolutionary changes to explain the observed pattern of character distribution. This is rigorous. It is also imperfect. The software can only work with the characters entered into the matrix, and the choice of which characters to include and how to score ambiguous cases introduces researcher judgment at every step. Different researchers scoring the same specimens differently can produce genuinely different trees. For hell ants, this has been the source of persistent disagreement. Some analyses recover them as the most basal, earliest branching lineage within ants, separated from all other ant groups by a deep divergence. Others place them closer to specific crown ant subfamilies, suggesting a more recent divergence and a more complex relationship to the modern fauna. The disagreement is not a failure of the science. It is the science accurately representing uncertainty, the honest output of a method working at the edge of its resolution. The tree is still being drawn. Each new specimen adds characters. Each new analysis adds resolution. The picture sharpens slowly the way a photograph develops, emerging from uncertainty towards something that eventually might be called clear. Science is done by people, and the science of hell ants is done by a very small number of people. The community of researchers who have published primary research specifically on Haidomyrmex could in any given year fit comfortably around a single conference table. This is not a criticism. It is a reflection of the material. There are only so many specimens, only so many amber collections to work in, only so much career space in academic entomology for a specialization this narrow. Rasnitsin and Glusky established the genus. Subsequent researchers, including Philip Barden at the New Jersey Institute of Technology, who has become one of the most prolific contributors to hell ant science in recent years, have extended the work considerably. Barden's lab has described multiple new hell ant genera and species-applied micro-CT scanning to hell ant specimens, and produced some of the most detailed biomechanical analyses of the trap apparatus. The 2020 paper describing the Haidomyrmex predation specimen was a product of this lab's work. Other contributors come from China, where proximity to the amber source material and strong institutional investment in Cretaceous paleontology have made Chinese researchers increasingly central to the field. European and North American museum researchers have contributed through work on their own collections. The network is international, loosely connected, driven by shared access to rare material. What these researchers share beyond their subject is a tolerance for uncertainty. Hell ant science is built on incomplete specimens, contested phylogenies, and inferences that may be revised by the next discovery. The researchers who stay in it are the ones who find that uncertainty interesting rather than frustrating, who can hold an open question for years without needing it resolved, who understand that the amber's silences are as informative as its revelations, and who keep coming back to the specimens regardless because the specimens keep offering something new. Consider the epistemological situation. You want to understand an organism, its ecology, its behavior, its evolutionary relationships, its place in the history of life. Normally, this work is supported by large sample sizes, hundreds of specimens from dozens of localities, statistical analysis of variation, comparison across populations and time periods, the kind of data density that allows confident conclusions. For Haidomyrmex specifically, you have fewer than a dozen well-documented specimens. No two of them are from the same colony, or if they are, there is no way to know it. None of them is a complete, undamaged individual in an unobstructed amber matrix. Every conclusion you draw is based on fragmentary, irreplaceable, non-renewable data, and every conclusion carries the implicit acknowledgement that a single new specimen could revise it. This is science at the edge of the possible. It is not unusual in paleontology. Many extinct organisms are known from single specimens, or from fragments so partial that the organism's basic body plan is uncertain. But it produces a particular kind of intellectual humility in the researchers who do it. You cannot be overconfident when the entire evidentiary base for your claims fits on a desk. You cannot dismiss alternative interpretations when the data genuinely supports more than one reading. What you can do is be precise. Precise about what the evidence shows, precise about what it does not show, precise about the inferential steps between observation and conclusion. The best Hellant papers are models of this precision, careful, explicit about uncertainty, honest about the limits of the material, while still drawing the conclusions the evidence supports. There is something almost philosophical about it. An entire research program, an entire career in some cases built on a handful of golden fragments, each one irreplaceable, each one, still, after all the scrutiny, holding something that hasn't been fully read. The scientific literature on Hellants is not voluminous. It is a collection of perhaps a few dozen primary research papers, spanning roughly 2 decades of serious systematic work. Each one, a careful addition to a structure that began with the 2003 description and has grown incrementally since. The pattern of accumulation is characteristic of amber paleontology. A new specimen is discovered in a collection in a dealer's stock in a previously unexamined piece of amber. It is described, its features are compared to known material, and if it represents something new, a paper is written. The paper adds to the character matrix available for phylogenetic analysis, adjusts the known morphological range of the group, and sometimes raises new questions that the specimen itself cannot answer. Occasionally, a paper does more than add to the accumulation. The 2020 predation specimen paper was one of these, a specimen so informative, a conclusion so direct, that it shifted the whole field's confidence level on a question that had previously been addressed only through inference. The trap was real, proven. That paper closed a question that earlier papers had only approached. Between those landmark moments, the literature proceeds by accretion. A new genus here, a revised phylogenetic analysis there, a micro-CT study that adds 3-dimensional detail to a previously described specimen, a review paper that synthesizes the accumulated knowledge and identifies the remaining gaps. Reading through this literature chronologically is an interesting experience, not unlike watching a photograph develop, as mentioned before, but more halting. There are long gaps between significant advances. There are papers that raise questions and are followed years later by papers that don't quite answer them. There are revisions of earlier conclusions that require rereading everything that came before in light of what came after. The knowledge grows, and it grows in the only way small data science can grow, carefully, incrementally, with each step earned by evidence, and each conclusion held with the appropriate degree of tentativeness for a field working at the very edge of what the material allows. Scientific illustration is not decoration. In paleontology, it is a form of reasoning, a process of integrating all available evidence into a visual hypothesis about what an animal looked like, how it held itself, what it was doing. A good scientific reconstruction of an extinct organism is a paper in visual form, with all the same requirements for evidence and the same acknowledgement of uncertainty. Hellant reconstructions have been produced by several scientific illustrators working in collaboration with the researchers who described the specimens. The most widely circulated images, the ones that appear in science, journalism, and popular accounts, show Haidomyrmex or its relatives in lateral view. The mandibles extended, the clypeal horn prominent, the body in a posture consistent with what the amber specimens show. These images are careful. The mandible geometry follows the actual measured curvature of the specimens. The body proportions are scaled from the available data. The surface texture, the fine details of the cuticle, the eye facets, the antennal segments reflects what microscopy reveals. Nothing is invented for drama, and yet every reconstruction is necessarily a hypothesis. The coloration hell ants are shown in amber-toned brown or in darker tones, suggesting a heavily sclerotized cuticle is inferred from the cuticle's preserved appearance and comparison to living ants with similar ecology. The exact posture of the antennae at rest, the precise angle of the legs during patrol, the way the body sits relative to the surface it walked on, these are informed guesses, constrained by anatomy, but not determined by it. The reconstructions are the public face of the science. They are what most people encounter first, before the papers, before the technical descriptions, before the biomechanical analyses. They do their job when they are honest about what they know and careful about what they don't. The best ones are both visually compelling and epistemically humble, a difficult combination to achieve, and worth appreciating when it is. A forensic anthropologist can look at a skeleton and read a life in it. The healed fractures that record old injuries, the bone density that reflects years of physical labor, the wear patterns on joint surfaces that map habitual postures, repeated movements. The skeleton is not just bones. It is biography written in calcium. An amber inclusion is similar, though the biography it holds is measured in moments rather than years. A trained morphologist looking at a hell ant specimen in amber reads information that is invisible to the untrained observer, not hidden exactly, but requiring the context of comparative anatomy and behavioral biology to decode. The angle of the antennae tells something about the animal's arousal state at the moment of trapping. Relaxed antennae fold differently than alert ones. The position of the tarsi, the foot segments on specimens where they are visible, gives information about the surface texture the ant was walking on and the grip configuration it was using. The attitude of the gaster relative to the thorax reflects whether the animal was in a defensive or neutral posture. The specific orientation of the head, not just its general forward tilt, but the precise rotational angle, carries information about what direction the animal was facing relative to its direction of travel. None of this is definitive. All of it is probabilistic. But the accumulation of probabilistic readings across multiple specimens produces a portrait, an approximation of the hell ant's behavioral repertoire that goes beyond what the anatomy alone can establish. The frozen body speaks to someone who has learned its language. It speaks slowly. It speaks in whispers. But it speaks, and the researchers who have spent years listening have assembled from those whispers a picture of a living animal moving through a living world, incomplete, uncertain, and more real than any reconstruction built from nothing could ever be. The hell ant story is not closed. It is actively unfolding, and the rate of new discovery, new species, new genera, new specimens of known taxa has been sustained across the decades of systematic study. The reason is partly the size of existing amber collections. Burmese amber has been collected in large quantities, and the material held in museums, universities, and private collections worldwide has not been exhaustively examined. A piece of amber purchased for its aesthetic quality held in a private collection for years may contain an undescribed species or an undescribed genus that no scientist has yet seen. When such material enters the scientific domain through purchase, donation, loan, or the publication of private collections, new species regularly result. The reason is also partly technological. Micro-CT scanning, which generates three-dimensional digital models of amber inclusions without physically modifying the specimen, has made it possible to examine the internal features of inclusions that were previously inaccessible, the undersides of trapped specimens, the features obscured by the amber matrix in direct optical examination, the three-dimensional geometry of structures that appear ambiguous in two-dimensional views. Specimens that were described decades ago on the basis of limited optical examination are being re-examined with new tools and the new examinations are producing new information. New hell ant species have been described in nearly every year of active research. Some represent genera already known, additional species of Haidomyrmex or Haidomyrmex, expanding the known morphological range of established taxa. Others represent entirely new genera, new branches of the hell ant tribe, new variations on the trap design, new windows into the ecological diversification of the group. The archive is not exhausted. The amber holds more than has yet been read, and the reading continues. Each new hell ant specimen is a data point. Individually, it adds what it adds: a new species description, a new character state, a new morphological variant to place in the matrix. Collectively, the specimens accumulate into something larger than any individual piece of amber can hold. The compound picture that is assembling across 2 decades of hell ant research is a picture of an adaptive radiation. Not a single species, not a single experiment, but a whole clade, a whole branch of evolutionary history that explored a specific ecological space with considerable thoroughness. The variation across hell ant genera is not random noise. It is the signal of a lineage actively diversifying, filling available niche space, refining and adjusting a core design across millions of years and multiple ecological contexts. The picture also includes the limits of the radiation. Hell ants are diverse within their trap design, but they do not extend beyond it. There is no hell ant that abandoned the upward jaw and became a seed harvester. There is no hell ant that developed the fungus farming behavior that would later make leafcutter ants among the most ecologically significant organisms in the American tropics. The trap was the identity of the clade, and the clade did not escape it. This is a pattern specialization that enables success and constrains flexibility that recurs throughout evolutionary history. It is visible in the hell ants with unusual clarity because the amber preserves the anatomy so faithfully, because the trap design is so unambiguous, because the absence of the design from all subsequent ant evolution is so total. Each new specimen adds a data point. What the compound picture shows with increasing confidence is a lineage that committed fully to one idea, hunted brilliantly within its constraints, and then stopped completely when those constraints became insurmountable. A complete story told in golden fragments, still being assembled piece by careful piece. The individual hell ant is relatively speaking well known. The hell ant colony is almost entirely unknown. This gap is not a minor omission. Ants are social organisms. They do not exist in any ecologically meaningful sense as individuals. An ant worker is a unit of a superorganism, its behavior shaped by the colony's needs, its physiology calibrated to its caste role, its entire existence meaningful only in the context of the collective. Understanding the individual ant without understanding the colony is like understanding a neuron without understanding the brain. Possible, informative, but radically incomplete. For living ants, colony structure is studied directly by excavating nests, by rearing colonies in laboratory observation chambers, by tracking individual workers with paint marks or RFID tags. For hell ants, none of this is possible. The colony is not preserved. The nest is not preserved. The queen, if hell ants had a morphologically distinct queen caste, has never been identified in amber. Were hell ant colonies large or small? The answer has implications for everything: for the species' ecological impact, for its hunting strategy, for its vulnerability to environmental disruption. Large colonies buffer against individual loss. Small colonies are more vulnerable. A highly specialized hunter with a small colony is a fragile ecological unit, easily destabilized by disruption to its prey base. Did hell ants have worker castes? Morphologically distinct groups of workers performing different functions? No polymorphic workers have been identified in Haidomyrmex, but absence of evidence is not evidence of absence when the specimen pool is this small. Perhaps all workers were similar in size and form, perhaps not. The nest is gone. The colony is gone. The social architecture that gave individual hell ant behavior its context gone without a trace, not even amber to hold it. The individual is preserved with extraordinary fidelity, and the society it belonged to is entirely invisible, as though the amber could hold the neuron, but not the mind. There is a practice in amber science that has no formal name but is recognized by everyone who does it. It is the practice of sitting with an open question, not forcing a conclusion, not reaching past the evidence, holding the uncertainty without filling it, because filling it with something unsupported would be worse than leaving it empty. This is harder than it sounds. Humans are pattern-completing animals. We fill gaps. We reach for the most available explanation and treat it as adequate. In everyday life, this is efficient. In science, especially in a field where the evidentiary base is small, irreplaceable, and incapable of being augmented by new experiments, it is dangerous. The hell ant researchers who have done the most careful work are distinguished partly by what they don't claim. They don't claim certainty about the prey identity when the evidence supports probability. They don't claim a definitive phylogenetic position when the analysis produces competing trees. They don't reconstruct behavior beyond what the frozen postures and anatomical features directly support. This restraint is not timidity. It is precision, and it is in its own way a form of respect for the material, for the uncertainty, for the questions that the amber has not yet answered and may never answer. What does it feel like practically to do science this way? To spend years studying an animal that cannot be observed, cannot be experimented on, cannot be asked to repeat its behavior for a camera? Researchers who have spoken publicly about this describe something that sounds at its best like a particular quality of attention, a way of looking at incomplete evidence with complete focus, finding what is there without inventing what isn't, and returning to the specimens again and again, because the specimens, however limited, are still the most direct contact available with a life that was fully real. The amber is patient. The questions it holds have waited 99 million years already. They can wait a little longer for the right tools to read them, and in the meantime they are held with the same care, the same precision, and the same quiet wonder that has characterized the best of this science from the beginning. Every lineage has a last member, a last individual in a last colony in a last season, after which the design is gone, the trap is gone, the upward jaw exists nowhere in the world. For hell ants, that last member lived sometime in the late Cretaceous, and the amber record can only approximate when. The youngest confirmed hell ant specimens come from amber deposits, dated to approximately 78 to 99 million years ago. No hell ant has been found in amber younger than the late Cretaceous. No hell ant has been found in any post-Cretaceous deposit. The absence is not absolute proof of extinction. At the Cretaceous boundary, absence from the fossil record can reflect preservation gaps as much as actual disappearance, but the pattern is consistent and has held across decades of expanding amber study. The working conclusion is that hell ants did not survive past the Cretaceous. They were gone before the world that followed the great extinction took shape. Whether they went gradually declining over millions of years as ecological conditions shifted, or relatively suddenly as part of the end Cretaceous disruption, is not known. The resolution of the amber record is not fine enough to distinguish between a gradual decline and a rapid one. What the amber record gives is a before, a world with hell ants in it, preserved in gold, documented, partially understood. What came after is silence. Not the silence of absence. The ant lineage continued and went on to build the most ecologically dominant group of terrestrial animals in Earth's history. But the silence of a specific design tried for tens of millions of years, and then gone, permanently, without sequel. 66 million years ago, something hit the Earth. The object, an asteroid roughly 10 to 15 kilometers across, comparable in width to a mid-sized city, struck what is now the Yucatan Peninsula of Mexico at approximately 20 kilometers per second. The impact released energy equivalent to billions of nuclear weapons simultaneously. The immediate effects, the fireball, the earthquake, the tsunami, were catastrophic on a regional scale. The global effects were worse and slower. The impact ejected enormous quantities of material into the upper atmosphere. The material blocked sunlight. Photosynthesis collapsed globally. The food webs built on photosynthesis, which is to say all food webs, were destabilized from the bottom up. Temperatures dropped. Acid rain fell. The darkness lasted months. The recovery took thousands of years. The result was the Cretaceous-Paleogene mass extinction. The event that ended the non-avian dinosaurs collapsed. Marine ecosystems drove the extinction of roughly 3/4 of all species on Earth and reset the trajectory of life on land in ways that still shape the world today. Hell ants were already gone before this event if the amber record is read correctly. They were part of an earlier, slower erosion, a gradual diminishment that preceded the catastrophe rather than being caused by it. But the KPG boundary is the context for their disappearance. Nonetheless, the end of the chapter they lived in, the closing of the Cretaceous world that had supported them. However, gradually that closing had begun. The asteroid ended a world. The hell ants were already watching it end. The question of whether any hell ant lineage survived past the Cretaceous-Paleogene boundary, even briefly, even in a refugium, even in diminished form, cannot be definitively answered with current evidence. The absence of hell ant fossils in Paleogene deposits is real. Amber deposits from the Eocene Baltic amber, Dominican amber, have been extensively studied and no hell ant has been found in them. The ant fauna of Baltic amber, dated to roughly 34 to 48 million years ago, is dominated by lineages recognizable as ancestors of modern ant subfamilies. It is taxonomically a modern-looking fauna. The crown ant radiation clearly established the stem group experiments over. No upward jaws, no clypeal horns, but absence from the fossil record is not equivalent to absence from the world. The amber record is not continuous. There are gaps, periods, and regions where amber deposits either did not form or have not been studied. A lineage could in principle have persisted in a region or during a period unrepresented in the amber record, and left no fossil trace simply because the conditions for preservation were absent. The probability is considered low. The geographical range of the hell ant record, spanning multiple continents, suggests the group was widespread in the Cretaceous. A widespread group that goes extinct typically does so because its ecological requirements disappear broadly, not because it is missed by preservation in every region simultaneously. The more parsimonious interpretation is that the hell ants were genuinely gone by the end of the Cretaceous or shortly after, and that the absence from Paleogene deposits reflects absence from the world rather than absence from the rasa record. But paleontology is a field in which single specimens revise conclusions, and the conclusion here rests on an absence, the most fragile kind of evidence. It holds for now because nothing has contradicted it. The rise of flowering plants is one of the most consequential ecological transitions in the history of terrestrial life. It was not a sudden event, it played out over tens of millions of years, accelerating through the mid-Cretaceous and completing its broad transformation of terrestrial ecosystems well into the Paleogene. But its effects on insect communities were profound, and those effects bear directly on the question of why hell ants disappeared. Flowering plants created new ecological opportunities for insects. New nectar sources, new pollen sources, new fruit resources, these drove diversification in the insects that could exploit them. Bees, butterflies, moths, beetles, flies, the groups that became most ecologically prominent in the modern world are almost without exception the groups that formed tight associations with flowering plants. The angiosperm revolution was simultaneously an insect revolution. But every revolution displaces something. The insect communities of the pre-angiosperm Cretaceous, the dense, complex fauna of soft-bodied larvae, early flies, and primitive herbivores that fed on ferns and cycads were restructured by the spread of flowering plants. Not destroyed, but reorganized. The specific prey community that the hell ant trap was calibrated to may have been part of that restructured world. If the larvae and soft-bodied insects that hell ants targeted were themselves dependent on the fern-dominated understory, if their populations were tied to plant communities that the angiosperms were replacing, then the hell ants' prey base may have eroded gradually as the forests changed around it. The trap was unchanged. The target was disappearing. And an unchanged trap aimed at a disappearing target is in evolutionary time a lineage writing its own conclusion. The relationship between a specialist predator and its prey is not a relationship between equals. The predator depends on the prey for energy, for the reproductive success that keeps its lineage going. The prey does not depend on the predator in the same way. The prey has other pressures, other predators, other reasons to persist or decline. The asymmetry means that when prey populations fall, specialist predators fall with them and often faster. For the hell ant, this asymmetry was built into the trap design. A jaw that cannot pivot, a horn that cannot be repurposed, a hunting system calibrated to a specific prey type. These are the features of a specialist that has committed. The commitment was successful for tens of millions of years, which means the prey was reliably present for tens of millions of years. The commitment became fatal when the prey was no longer reliable. The prey landscape argument does not require a sudden prey collapse. A gradual decline, a slow erosion of population density, a shift in habitat distribution, a reduction in the seasonal predictability of prey availability would be sufficient to destabilize a specialist predator operating on narrow margins. A colony of hell ants that cannot find enough prey to raise the next generation of workers is a colony in decline. A declining colony produces fewer reproductives. Fewer reproductives means fewer new colonies. Fewer new colonies means the population contracts. Contraction, if sustained, leads to extinction, not dramatically, not suddenly, but through the accumulated arithmetic of reproduction failing to replace mortality season after season, generation after generation, until the last colony fails and there are no more. The trap still worked. The prey was simply no longer there in the numbers the trap required. And so the trap, however elegant, however refined, however perfectly suited to a world that had existed for millions of years, became an instrument without a purpose, a solution to a problem the world had quietly stopped having. The flowering plant hypothesis is the most widely discussed explanation for hell ant extinction, but it is not the only one, and its proponents do not claim it is sufficient on its own. Extinction is rarely monocausal. It is typically the product of multiple pressures converging, each one manageable alone, lethal in combination. Climate change is a candidate pressure. The mid to late Cretaceous saw significant climate variability, not the rapid anthropogenic warming of the present, but geological scale shifts in temperature and precipitation patterns that reorganized vegetation zones and disrupted established ecological communities. A specialist predator with narrow habitat requirements would be more vulnerable to these shifts than a generalist capable of adjusting its diet and behavior. Competition is another candidate. The late Cretaceous saw the diversification of crown group ants, the lineages that would go on to dominate the modern world. These new ant lineages were for the most part more ecologically flexible than the hell ants, capable of exploiting a wider range of food sources, nesting in a wider range of substrates, operating across a wider range of environmental conditions. If crown group ants were moving into the ecological space that hell ants occupied, the competition for nest sites, for territory, for the prey, community itself would have added pressure to an already stressed lineage. Disease, parasitism, and stochastic effects, the random bad luck of small populations, are always in the background. A lineage already declining for other reasons becomes increasingly vulnerable to disruptions that a larger, more robust population would absorb. The hell ants probably did not die from one cause. They died from several operating across a timescale of millions of years, each one reducing the margins until the margins were gone, until the last colony in the last forest with the last working trap could not find enough prey to make the next generation. Evolution is not directed. It does not move toward a goal. There is no endpoint. It is aiming for no optimal configuration it is converging upon. The history of life is a history of contingency of outcomes that were not inevitable, of roads taken and roads not taken, of lineages that succeeded and lineages that failed, and no overarching logic that separates the two except the local, temporary, probabilistic judgment of survival and reproduction. Hell ants are a road not taken, a design tried successfully for tens of millions of years, and then abandoned, not by choice, but by circumstance. The upward jaw, the clypeal trap, the vertical axis predatory system, these are not inferior to the horizontal jaw of modern ants. They are different. They worked in their context. They failed in a different context. The context changed, and the design went with it. What this means for understanding ant evolution is significant. It tells us that the modern ant body plan, the design that went on to produce 14,000 species and colonize every continent, was not the only viable design. It was one of several experiments running simultaneously in the Cretaceous, and it won not because it was superior in any absolute sense, but because it was more flexible, more applicable across a wider range of ecological contexts, more capable of adjusting to a changing world. The hell ant was a masterpiece of narrow purpose. The modern ant is a masterpiece of broad applicability. Both are masterpieces. Only one survived. This is the deepest lesson the hell ant offers, not about ants exactly, but about evolution itself. Brilliance is not enough. Precision is not enough. A perfect solution to a disappearing problem is still, in the end, a problem. Spend enough time with the hell ant literature, and a specific quality of loss becomes apparent. It is not the loss of a species or even a genus. It is the loss of an idea, a functional idea, a working principle, a design logic that was developed over millions of years of evolutionary refinement and then erased without remainder. The upward jaw trap is gone. Not dormant, not reduced, not preserved in vestigial form in some obscure living lineage. Gone. The 14,000 living ant species carry no trace of it, no hint that evolution once explored this direction, no feature in even the most primitive living ant that gestures toward the vertical closure. The design was not incorporated into anything that survived. It was abandoned completely. This is unusual in evolutionary history. Most functional innovations leave traces, modified, reduced, repurposed, but traceable. The hell ant trap is traceless in the living fauna, which means it was not the ancestor of anything currently alive. It was tried. It worked. It ended. What was lost practically is a predatory strategy, a way of catching a specific kind of prey in a specific kind of forest with a specific kind of precision that no living ant possesses. Whether that strategy would be useful today, whether the ecological niche it filled is currently vacant or has been filled by something else entirely, is not a question with a clean answer. The niche may be occupied now by other small predators, centipedes, spiders, predatory beetles, that evolved their own solutions to the problem of catching soft-bodied insects in forest environments. The hell ant's specific solution is gone. The problem it was solving may or may not still exist in some form in some forest. On a tree trunk somewhere unsolved in the particular way, the hell ant once solved it, and solved instead, if at all, by something that has no idea what came before. The ants that inherited the Cretaceous world, the lineages that diversified through the Paleogene and built the modern ant fauna, succeeded by doing in many cases the opposite of what the hell ants did. Where hell ants specialized, the survivors generalized. Where hell ants committed to a single prey type and a single hunting strategy, the survivors remained flexible, able to eat seeds, or fungus, or other insects, or nectar, or carrion, depending on what was available. The Myrmicinae, the subfamily that today contains roughly a third of all living ant species, includes seed harvesters, fungus, farmers, generalist omnivores, and specialized predators. The flexibility within the subfamily is the point. No single ecological commitment defines it. It occupies many niches rather than one, and when any single niche becomes unavailable, the lineage does not collapse, it shifts. The Formicinae, the subfamily that includes the familiar garden ants of temperate regions, developed trophallaxis, the exchange of liquid food between individuals, to a high degree. This behavior enables colonies to pool resources to support non-foraging members, to buffer against individual foraging failures. A colony that can share resources is a colony more resistant to local prey shortages. These are not better designs than the hell ant trap. They are different designs suited to different demands. The hell ant's demand was precision. The surviving lineage's demand was resilience. In a world that was changing, in a world where the specific conditions that supported precision were being replaced by conditions that rewarded resilience, the resilient lineages survived and the precise one did not. The lesson is not that specialization is wrong. It is that specialization is a bet. The hell ants bet on the stability of their world. For tens of millions of years the bet was right. Then the world changed, and the bet was called. The hell ant is not unique in evolutionary history as a dead end. The history of life is dense with them. Lineages that flourished for millions of years filled ecological niches with precision and success, and then ended, leaving no descendants and no living memory of their existence except in the rock and the resin. The non-avian dinosaurs are the most famous example, dominant terrestrial vertebrates, for 150 million years, gone at the KPG boundary, their ecological roles eventually filled by the mammals that survived. The trilobites, extraordinarily diverse marine arthropods that dominated the Paleozoic seas for 270 million years, gone at the end of the Permian, replaced by other marine invertebrates that evolved into the niches they had occupied. The blastoids, the graptolites, the eurypterids, lineages that for their time were as successful as anything alive today and are now entirely absent. Each dead end is a lesson in contingency. The lesson is that success is not permanent, that a lineage can be successful for longer than the entire history of modern humans, and still end if the conditions that made it successful change. The hell ant hunted with a perfect trap for tens of millions of years. It was by any reasonable measure a successful organism, durable, widespread, diversified, ecologically significant in its forest community. And it is gone. Completely irreversibly gone, surviving only in the amber windows that chance preserved and science has learned slowly to read. Contingency is the deepest truth of evolutionary biology. The world is not designed to maintain the things it has made. It makes them, it uses them, and when the conditions change, it lets them go without ceremony, without record, without the slightest indication that what is ending was anything other than ordinary, which it was, and which is precisely the 12th point. The amber that holds the hell ant was not found in a laboratory. It was not extracted by scientists with careful tools and institutional oversight. It came out of the ground in the Hukong Valley, a region that has been for much of the period of intensive amber study an active conflict zone. Kachin State has been the site of armed conflict between the Kachin Independence Army and the Myanmar military for decades, with periods of ceasefire and periods of renewed fighting that have displaced hundreds of thousands of people and produced well-documented human rights abuses. The amber mines operate within this context in a region where civilian populations have been caught between armed factions, where forced labor has been reported, where the proceeds of resource extraction have funded military operations. The workers who extract amber, who dig the shallow mines, who sort the raw material, who carry it to dealers, are working in conditions that range from difficult to dangerous for compensation that reflects the asymmetry of a resource trade-in, which the market value of the material increases enormously as it moves from the valley to the collections. A piece of amber worth a few dollars at the mine may be worth hundreds or thousands by the time it reaches an institution willing to pay for scientific access. This is not a peripheral fact about Burmese amber science. It is a central one. Every specimen of Haidomyrmex in every museum collection worldwide arrived through this supply chain, through a region of conflict, extracted by people whose labor conditions are not documented in the papers that describe the specimens. The scientific knowledge built on this material is real. The human cost behind its extraction is also real. Both facts are true simultaneously, and neither cancels the other. The scientific community's response to the ethics of Burmese amber has been neither uniform nor resolved. It has been a genuine debate, serious, ongoing, and without a clean conclusion among researchers who care about both the science and the human context it operates within. In 2017, as the political situation in Myanmar deteriorated and evidence of conflict zone mining conditions became more widely documented, the Society of Vertebrate Paleontology issued a statement recommending that its members not purchase or describe new Burmese amber material until the situation could be assessed. Other organizations followed with their own guidance. Some individual researchers announced they would no longer work with newly acquired material. The debate that followed exposed genuine tensions. On one side, the argument that purchasing amber funds conflict and exploitation, that scientific demand drives the market, and reducing that demand reduces the harm. On the other side, the argument that the material is being mined regardless of scientific demand, that refusing to study it does not help the workers who extract it, and that withholding scientific attention from specimens already in collections serves no one. Some institutions adopted policies distinguishing between material already in collections before a certain date, considered acceptable to study, and newly acquired material, which they declined to accept. Others drew the line differently. Some continued purchasing material, arguing that the scientific value justified the engagement. The debate has not produced consensus, and the policies vary considerably across institutions and national scientific communities. What is clear is that the question cannot be bracketed. It cannot be set aside as separate from the science. The specimens are inseparable from their origin, from the valley, from the conflict, from the hands that found them, and the science built on them carries that origin, whether the papers acknowledge it or not. The specimens are already there. In museum drawers, in university collections, in research institutions on multiple continents, the hell ant specimens and thousands of other Burmese amber inclusions already extracted, already purchased, already described in the literature. The chain of custody that brought them to their current locations cannot be undone. This creates a specific ethical situation with no clean resolution. The knowledge built on these specimens is real, peer-reviewed, published, reproducible, in the sense that other researchers can examine the same specimens and reach the same conclusions. The biomechanics of the hell ant trap the phylogenetic analyses. The predation specimen from 2020. This is genuine scientific knowledge, produced through rigorous methods, contributing to the human understanding of evolutionary history. It was also produced using material whose extraction involved human suffering in a conflict zone. The knowledge and the cost coexist in the same object. The amber in the museum drawer is simultaneously a scientific archive of extraordinary value and a product of conditions that no ethical framework endorses. What institutions do with this reality varies. Some acknowledge it in their publications, a brief statement noting the provenance issues and the ethical complexity. Others do not. Some have developed guidelines for future acquisitions that aim to prevent further accumulation of ethically problematic material while continuing to work with existing collections. The field is slowly developing a more explicit engagement with these questions, not because the engagement is comfortable, but because the discomfort of ignoring them has become harder to sustain than the discomfort of addressing them. The specimens are there. The knowledge is real. The cost was paid by someone who will not appear in any paper's acknowledgements section, and who had no say in whether the amber they extracted would end up in a journal article about a 99-million-year-old ant. Behind every specimen in every collection there is a person, not a researcher, not a curator. A miner, someone who dug into a hillside in the Hukong Valley, sifted through sediment, recognized the amber-colored fragment among the grey rock, and extracted it with their hands. Someone for whom the value of that fragment was measured in what it would bring from a dealer, not in what it would eventually reveal about Cretaceous predator anatomy. The miners of the Hukong Valley are not a homogeneous group. Some are local people for whom amber extraction is seasonal supplementary income. Some are migrants from other regions drawn by the amber trade's economic activity. Some work in conditions of relative autonomy. Others work in conditions of debt, bondage, or coercion. The range of circumstances is wide, and the documentation of those circumstances is incomplete. The valley is not easily accessed by outside observers, and the people within it are not always in a position to speak freely about their conditions. What is documented is the general context, a conflict zone, a resource extraction economy, a trade whose profits flow primarily outward and upward, while the labor that generates them remains local and poorly compensated. The amber trade has made some people wealthy. The miners who make the trade possible have not been among them. This is not unique to amber. It is the structure of extractive economies, generally a structure so familiar, so persistent, so thoroughly embedded in the global economy that it becomes easy to treat as background. The hell ant in the amber does not require this background to be scientifically interesting, but understanding the full cost of the knowledge it has provided requires seeing the background clearly, even when the clarity is uncomfortable, even when there is nothing simple to do about what it shows. The researchers who work with Burmese amber are not naive about this tension. The ones who engage with it honestly describe something that does not resolve a persistent discomfort that coexists with the genuine excitement of the science that does not go away when a new specimen yields a new discovery, that sits in the background of every paper and every microscope session and every conference presentation. Some researchers have chosen to stop acquiring new material to work only with what is already in institutional collections and to state this choice explicitly in their publications. This is a meaningful decision. It forecloses certain research directions. It limits access to new specimens. It accepts a constraint on the science for the sake of a principle. The constraint is real. So is the principle. Others continue to work with new material, arguing that the scientific value is sufficient justification or that the alternatives material going to private collectors, specimens never studied, knowledge never produced, are worse outcomes. This argument is also coherent. It is also in the view of those who have chosen differently insufficient. The tension is not going to be resolved by more careful thinking. It is a genuine conflict between values, the value of knowledge, the value of human well-being, the complexity of a supply chain that operates in a conflict zone and connects the deepest past to the most urgent present. What it requires is not resolution but acknowledgement, the honest recognition that both things are true, that the science is valuable and the cost is real, and that the people who extracted the material from the ground deserve to be part of the story of what the material contains, even if the papers that tell that story have not always remembered to include them. There is a smaller question beneath the human ethics question, quieter, less urgent, but worth asking in the spirit of the kind of attention this material deserves. What do we owe the hell ant? Not legally, not practically. That hunted and ate and reproduced and died in a world that was as real as this one, as detailed, as populated, as indifferent to its own eventual disappearance. An organism that did not know it would be preserved, did not know it would be studied, did not know that a piece of resin falling from a wound in a tree would catch it mid-step and hold it for 99 million years until something with microscopes and phylogenetic software came along and started asking questions. The hell ant owes us nothing. It was not preserved for our benefit. It was preserved by accident, held by chemistry and found by commerce before it reached science. What we owe it, perhaps, is the quality of attention it has received from the researchers who have spent careers on it, the careful, humble, precise attention that takes the evidence seriously, that does not overclaim, that holds the open questions open and returns to the specimens again and again, because the specimens are the only real contact available with a life that was fully real and is now fully gone. That quality of attention is not nothing. It is in the absence of any other form of acknowledgement, the closest thing to respect that a 99-million-year-old ant can receive, and the hell ant, in its amber drawer, in its frozen posture, in the last mid-step it will ever take, has received it from the people who looked most closely with the most care and wrote down what they found. Come back at the end to the amber. The piece sits in a drawer. It is small, the size of a large grape perhaps, or a flattened marble, golden with a slight cloudiness in one corner where the matrix is less pure, where bubbles caught when the resin was still liquid and have been there ever since. The surface is smooth, polished by whoever prepared it for study, the edges worn to a gentle roundness by the same handling that has moved it from collection to collection over the decades. Inside, visible under a hand lens, is the ant. You can see the general shape without magnification, a dark form, a few millimeters long, suspended in the amber at a slight angle. The head tilted forward, the mandibles, and even at low magnification, the wrongness of them is immediately apparent, the upward curve unmistakable. The narrow waist. The compact gaster positioned behind the thorax at the angle the amber caught it. The antennae are extended, forward. The legs are mid-stride. The animal was moving when the resin fell, and it is still moving in the sense that motion was the last thing it was doing, and the amber caught the motion and held it, and now the motion is the posture, and the posture is the specimen, and the specimen is what 99 million years of patience looks like when it is small enough to hold in your hand. This is the hell ant, not the concept, not the clade, not the biomechanical model. This small, golden, frozen thing, mid-step in a forest, that no longer exists, carrying a trap that nothing alive has replicated. Heading somewhere, It never arrived in a direction that the resin chose for it, and amber made permanent. It is here. It has always been here in the geological sense. And now, for a few centuries at most, it is also findable, held in a collection, accessible to the tools that can read it, available to the attention that can begin to understand what it was. Let the record be clear about what the amber does not hold. It does not hold the colony, the nest, the queen, the division of labor, the chemical communication that coordinated foraging, gone, not preserved, not recoverable from the specimens that exist. What social life looked like for a hell ant worker is entirely unknown, and may remain so regardless of how many new specimens are found. It does not hold the prey identity with certainty. The Haidomyrmex predation specimen gives a genus of prey a cockroach relative for one hell ant species. Whether Haidomyrmex specifically targeted the same prey type is inferred, not proven. The precise prey of the type species remains unknown. It does not hold the venom chemistry. What the hell ant injected, if it injected anything, how the venom worked, whether it paralyzed or killed or merely held, gone with the soft tissue, the glands, the biochemistry that amber cannot preserve. It does not hold the sound of the forest, the insect chorus, the calls of the organisms that move through the same canopy. The ambient acoustic environment of a mid-Cretaceous tropical forest at midday or at dawn. It does not hold the smell, the resin, the fern mulch, the humidity, the specific chemical landscape the hell ant's antennae were reading as it moved. It does not hold the duration of a single hunt, how long from first chemical detection to successful capture. It does not hold the failure rate, how often the trap missed, how often prey escaped, how often the ant returned to the colony without food. It does not hold the lifespan of a worker or the size of a typical colony, or whether hell ants were aggressive or cryptic when disturbed. These are not small emissions. They are the substance of a life. The amber holds the form. The life that filled the form is gone, and no instrument yet built can recover it. This is the honest accounting, offered not to diminish what the amber gives, which is extraordinary, but to hold the full picture clearly, to resist the temptation to complete the portrait beyond what the evidence supports, to sit with the gaps as honestly as the specimens themselves sit with them. Science does not stand still, and the limits of what can be read from amber today are not necessarily the limits of what will be readable in 20 years, or 50 or 100. Micro-CT scanning has already extended the readable surface of amber inclusions far beyond what optical microscopy could reach, revealing three-dimensional geometries, internal surfaces, structural details that earlier researchers could not access. The technique continues to improve in resolution and speed in the software used to render and analyze the resulting data. Synchrotron radiation, a more powerful form of X-ray imaging, available at large-scale particle physics facilities, offers resolutions approaching the cellular scale in ideal specimens. Whether cellular-scale imaging of amber inclusions would reveal soft tissue traces, muscle fiber orientations, or organ remnants is a question currently being tested on exceptionally well-preserved specimens. Early results have been promising in some cases, not in others. Proteomics, the analysis of preserved proteins rather than DNA, represents another frontier. Proteins are more durable than DNA, and traces of original protein chemistry have been reported in some exceptionally preserved fossils from much older than the Cretaceous. Whether amber preservation is compatible with proteomic analysis at the resolution needed to yield meaningful biological information is an active research question. The answer is not yet known. Artificial intelligence applied to morphological analysis, machine learning systems trained on large data sets of insect anatomy, is beginning to assist with the identification and characterization of amber inclusions, potentially accelerating the processing of unstudied material in existing collections. Each of these methods is right now extending the frontier of what the amber can yield. Each new tool is a new question put to the resin, a new way of asking the material to give up something it has held patiently for longer than the questioner can fully comprehend. The amber is not finished speaking. It is waiting as it has always waited for the right question, asked with the right instrument, held with the right quality of attention. The hell ant's biography is not complete. It may never be complete. But it is longer today than it was 20 years ago, and it will be longer 20 years from now than it is today, and each addition, each careful evidence-supported, honestly uncertain addition, is a small act of recovery, of something returned from the deep past to the present briefly and incompletely and beautifully. There is a piece of amber in a drawer somewhere in the world. It is small. It is warm when you hold it. It has been in the dark for most of its existence, first under kilometers of sediment, then under the soil of a hillside in a conflict zone, then in the packaging of a dealer, then in the archival storage of a collection, and it will likely return to the dark when whoever is looking at it now sets it down and closes the drawer. Inside it is an ant that lived 99 million years ago in a forest that no longer exists, on a continent that has since moved, in a climate that has since changed, hunting prey whose identity is still not fully established, with a trap that nothing alive has ever repeated. It was moving when the resin caught it. It is still moving, in the only sense available to it, still mid-step, still forward-directed, still carrying the posture of an animal that had somewhere to go and was going there, antennae, reading the air jaws, ready, the geometry of the trap, intact and functional, and aimed at a world that had already by the time anyone found this ember been gone for longer than the human mind can hold. The hell ant does not know it is the last evidence of an entire way of being alive. It does not know it is evidence of anything. It was an ant. It was doing what ants do, moving through its world, following the chemical signals, doing the specific and remarkable thing its jaw was built to do, in the specific and unremarkable way that all living things do the things they are built for, without awareness of how extraordinary the ordinary is, until something preserves it and something else much later looks. We are the something else much later looking. With our microscopes and our phylogenetic software and our carefully written papers and our quiet, genuine wonder at a creature that was fully alive, fully itself, fully present in a world we will never see and can only approximate, held in gold, frozen mid-step, still waiting in its unhurried and vague, permanent way, to tell us something we do not yet have the tools to hear. It has time. It has always had time. The amber is patient in a way that nothing living can be patient, across extinctions, across geological epochs, across the entire span of everything that has happened since the resin fell. It will still be there when the drawer opens again. It will still be there when the next instrument is built, the next question asked. The next careful pair of eyes comes to the microscope and looks through the golden matrix at the frozen posture of a thing that hunted in the dark of a vanished world, and finds in that looking something worth the long wait.